Hello there, and welcome to Science for Sleep, where we take interesting questions, slow them down, and give them enough room to become pleasantly complicated without demanding that you stay awake for the answers. Tonight, we are heading into the early solar system to look for something that may no longer exist. Not a missing moon, not an asteroid that wandered away, not one of the distant objects beyond Neptune that occasionally appears in a headline and causes everyone to start arguing about the definition of a planet again. This is something much closer to home. A possible rocky world that may once have travelled around the Sun beyond Mars, remained there for hundreds of millions of years, disturbed the asteroid belt, helped send enormous numbers of objects toward the inner planets, and then disappeared. Scientists gave this hypothetical world a wonderfully simple name: Planet 5. And before we go any further, there is one useful detail to clear up. You may occasionally see Planet 5 described dramatically as a lost 10th planet, particularly when the idea escapes from scientific papers and wanders into popular discussions. But the V in Planet 5 is the Roman numeral for 5. It refers to the possibility that the early solar system once contained 5 terrestrial planets instead of the 4 rocky planets we have today: Mercury, Venus, Earth, Mars, and one additional world. That extra world has never been observed. No telescope has photographed it. No spacecraft has visited its remains. There is no old astronomical record describing a mysterious planet beside Mars, because if Planet 5 existed at all, it vanished billions of years before human beings appeared, before dinosaurs appeared, before complex animals appeared, and probably before Earth had settled into anything we would recognise as a pleasant place to spend an afternoon. Planet 5 is a scientific hypothesis, and that distinction is important. We are not beginning tonight with a forgotten historical planet that astronomers once saw and then somehow misplaced. Planets are fairly difficult things to misplace, particularly when they are several thousand kilometres across. Instead, we are beginning with a question raised by computer simulations and by a much older mystery written across the surfaces of the Moon and the other rocky worlds. Something happened in the early solar system. The Moon still carries the evidence. Look at a detailed image of its surface and you see craters overlapping craters, enormous impact basins, circular scars hundreds of kilometres wide, and landscapes that record an age when collisions were much more common than they are now. The inner solar system was once an unpleasant place to own property. Earth was being struck. Mars was being struck. Mercury was being struck. The Moon was being struck repeatedly by large objects travelling at tremendous speed. Some of those impacts were powerful enough to reshape entire regions. Scientists have spent decades trying to reconstruct exactly when those impacts happened, how intense the bombardment really was, and, perhaps most importantly for our story, where all of the impactors came from. Planet 5 was proposed as one possible answer, so tonight we are going to follow an unusual piece of planetary detective work. We will begin before the solar system looked anything like it does today. We will look at how planets formed, why young planetary systems are surprisingly untidy, and how an extra rocky planet might have survived between Mars and the asteroid belt without immediately causing trouble. Then the trouble begins, because in the Planet 5 hypothesis, the missing world does not stay politely in its original orbit forever. Its path gradually changes. Gravitational nudges accumulate. An orbit that was once relatively calm becomes unstable. The planet begins travelling through a region filled with smaller bodies. Asteroids are disturbed. Some are thrown onto new paths. Some begin crossing the orbits of Mars and Earth. The population of objects capable of striking the inner planets rises. And somewhere during all of this, Planet 5 itself is removed from the solar system we know. It may sound like an unusually elaborate way to explain a collection of old craters. Scientists, however, are used to working with missing things. Astronomy's full of objects that cannot be picked up, visited, or sometimes even seen directly. We know that black holes exist partly because of what happens around them. We discovered planets around distant stars by watching those stars move or dim. Neptune was famously predicted through the gravitational effects it had on another planet, before anyone deliberately observed it through a telescope. In planetary science, absence does not necessarily end an investigation. Sometimes absence begins one. And Planet 5 is a particularly interesting example because the evidence, if there is evidence at all, would not be a photograph of the planet. It would be consequences, an unusual pattern of impacts, the architecture of the asteroid belt, the present arrangement of the terrestrial planets, the probabilities produced by orbital simulations, perhaps a giant scar on another world, perhaps nothing conclusive at all. That last possibility will remain with us as well, because Planet Phi is not a settled part of solar system history. It is not something you will find listed between Mars and Jupiter in a standard diagram beside a helpful little arrow saying, "Former planet left approximately 4 billion years ago." It is one proposed solution to a difficult problem, and later work has tested whether the idea can actually produce the effects it was designed to explain. That makes the story more interesting, not less. There is something rather relaxing about science when it is allowed to say, "We don't know yet." You do not have to force the universe into a tidy answer before bedtime. You can simply examine the possibilities. So wherever you are listening tonight, I have a question for you. Where in the world are you? And if you happen to know, what can you see in the sky from where you are? Perhaps you're listening in a city where only the brightest stars manage to compete with streetlights. Perhaps you're somewhere quieter, where the Milky Way is visible as a pale band overhead. Maybe Mars is above your horizon. Maybe Jupiter is. Or perhaps the weather has contributed a thick layer of cloud, and the entire observable universe currently consists of the ceiling. That is perfectly acceptable too. There is something amusing about discussing a planet that may have vanished 4 billion years ago while lying in bed beneath a roof that prevents us from seeing even the moon. If you enjoy these slow journeys through science, you can give the video a like and subscribe to Science for Sleep. It helps more listeners find these long, quiet explorations, and it also tells the algorithm that, for reasons known only to itself, people apparently enjoy listening to several thousand words about extinct planets while trying to fall asleep, which seems like a healthy use of modern technology. Settle into whatever position is comfortable. You do not need to remember dates. There will be no examination in the morning, and if you fall asleep while Planet Phi is still safely orbiting beyond Mars, you can rest assured that celestial mechanics will continue without your supervision. Before we follow this missing world, though, it helps to understand why anyone proposed it in the first place. The idea was developed by planetary scientists John Chambers and Jack Lissower and presented in the early 2000s, while they were investigating the history of intense impacts in the inner solar system. Their model began with an assumption that sounds small but changes the story considerably. Suppose the early solar system did not finish forming with 4 terrestrial planets. Suppose it finished with 5. The additional planet would have occupied space beyond Mars and inside the main asteroid belt. In early versions of the idea, it began on an orbit around 1.8 to 1.9 astronomical units from the Sun. 1 astronomical unit is the average distance between Earth and the Sun, so Earth sits at 1 astronomical unit, Mars averages roughly 1.5, and this hypothetical world would have been somewhat farther out than Mars, but well inside the region dominated by the asteroid belt. It was not imagined as another Jupiter hiding in the neighbourhood. That would be difficult to overlook. Planet 5 was proposed as a relatively small terrestrial body, somewhere in the broad category of a planetary embryo or a small rocky planet. Computer experiments explored different masses and orbital arrangements. The important requirement was that this world had to perform a rather awkward balancing act. It needed to survive for a long time, then it needed to become unstable. That timing matters. If an extra planet formed beyond Mars and immediately crashed into something, it would simply become another event during the general chaos of planet formation. Interesting, certainly, but not especially useful for explaining a bombardment that may have occurred much later. The Planet Phi idea instead asks whether an additional terrestrial world could remain in a reasonably stable orbit for hundreds of millions of years before gravitational interactions finally pushed it into trouble. This is where the solar system becomes less like the familiar diagram from school and more like what it really is, a collection of moving masses constantly pulling on one another. Those pulls are usually small compared with the Sun's gravity. Earth is not in immediate danger of being dragged into Venus because Venus happens to pass nearby on the other side of the solar system. The planets follow remarkably stable paths on human timescales, but billions of years give tiny gravitational effects a great deal of time to accumulate. Orbital resonances matter. Repeated gravitational perturbations matter. A path that survives comfortably for 10 million years is not necessarily guaranteed to survive for 1 billion. This is one reason computer simulations are so useful. You can build a simplified solar system inside a computer, give the planets masses and starting orbits, and allow gravity to do what gravity does. Then you watch, not for an evening, for hundreds of millions of simulated years. Fortunately, the computer does not require hundreds of millions of actual years to complete the experiment. That would make peer review unnecessarily slow. Researchers can run many versions, change the mass of the hypothetical planet, move its starting position slightly, alter its eccentricity, run the system again, then again. Some arrangements collapse quickly, others remain stable. Some allow the extra planet to survive for surprisingly long periods before its orbit changes dramatically. That possibility is the doorway through which Planet 5 entered scientific discussion. Imagine the young solar system several hundred million years after the planets formed. Mercury is travelling close to the Sun. Venus and Earth occupy the middle region. Mars moves farther out. And beyond Mars is another rocky world. If you could somehow visit this period, Planet Fulva might not look unusual. There would be no label floating above it warning temporary. It would simply be another planet. It would rise and set in the skies of neighbouring worlds. It would complete orbit after orbit. Depending on its size and surface conditions, it might resemble some combination of Mars, Mercury, or the airless rocky bodies we see elsewhere. We cannot describe its surface confidently, because the hypothesis is primarily dynamical. The simulations concern mass, orbit, gravitational interaction, and survival. They do not tell us that Planet 5 had blue mountains, silver deserts, 3 moons, or a charming collection of volcanoes. Those details belong to fiction, unless evidence appears. The scientifically interesting part is its motion. For a long period, nothing spectacular may have happened. That is easy to overlook when discussing planetary catastrophe. We tend to imagine the early solar system as permanently violent, with planets colliding every few minutes and asteroids flying around like badly supervised fireworks. The reality was more gradual. Planet formation itself was violent, certainly. Large objects collided. Planetary embryos merged. Debris was scattered. But as the major planets emerged, much of the system became progressively calmer. Orbits cleared. Material was removed. The broad structure began approaching the arrangement we recognize. Planet 5, in the proposed scenario, would have been a leftover from that formation process. Not a visitor from another star, not a planet captured later, not a hidden object waiting beyond Neptune. It would have been born here. For a while, it would have belonged here as naturally as Mars did. This is what makes the idea so peculiar. When we picture the solar system, its layout feels permanent. Mercury, Venus, Earth, Mars, then the asteroid belt, then Jupiter. We learn the order early enough that it starts to seem less like a historical outcome and more like a rule. But there is no law saying the solar system had to end with exactly these planets. Planetary systems are products of formation, collisions, migration, ejection, and chance. The arrangement we see today is the surviving arrangement. That is not necessarily the same thing as the original arrangement. We already have strong reasons to believe that major worlds moved during the solar system's youth. The giant planets did not simply materialize at their present addresses and remain there forever. Modern models of planetary formation involve substantial migration and interaction. Small bodies were scattered. Some were absorbed by planets. Some collided with the Sun. Others were thrown into the distant reaches of the solar system or expelled entirely. Earth itself probably owes the Moon to an enormous collision early in its history, when a planetary body commonly called Theia struck the young Earth. So the general idea of losing a planet-sized object is not particularly outrageous. Planet formation is quite efficient at making large objects and then destroying, merging or ejecting some of them. What is unusual about Planet 5 is the proposed delay. It may have survived long after the most chaotic stage was over. Think about that for a moment. A world could exist for hundreds of millions of years, long enough for an enormous amount of geological history to occur, long enough that, had anyone been around to draw a map of the solar system, the map would confidently include 5 rocky planets. Then its orbit changes. The world begins entering territory it previously avoided, and after that the entire inner solar system may notice. There is a useful comparison here with the asteroid belt itself. People sometimes imagine the asteroid belt as a densely packed obstacle course, largely because films enjoy giving spacecraft something to dodge. In reality, the objects are separated by enormous distances. If you travelled through the main belt, you would not spend the journey frantically steering around tumbling rocks every 4 seconds. Several spacecraft have crossed it quite safely, but gravitationally, the asteroid belt is still sensitive. Objects there occupy a vast range of orbits. Jupiter strongly influences many of them. Resonances create gaps and unstable regions. A planet repeatedly passing through parts of that population could disturb some asteroids and alter their paths. The Planet Vive model makes use of exactly that possibility. The hypothetical world begins outside Mars. Later, as its orbit grows more eccentric, its path stretches farther from the Sun at one end and closer at the other. Eventually that orbit can cross regions occupied by asteroids. Now close encounters become possible. Planet 5 does not need to physically strike every asteroid. Gravity can do the work. An asteroid passing sufficiently near a planet can leave the encounter travelling on a very different orbit. Some objects could be pushed toward resonances. Others could become Mars crossers. From there, gravitational interactions could continue modifying their paths until a fraction became capable of reaching Earth and the Moon. One relatively small planet could therefore cause effects far beyond its own physical size. Imagine walking into an empty room containing a perfectly arranged set of billiard balls and gently moving one of them. Not a particularly dramatic event. Now imagine the table has no friction, every ball is constantly moving, and you return several million years later. Things become harder to predict. The analogy is imperfect, as billiard balls are not especially well known for orbital resonances, but it gives us the basic idea. Planet 5 would be an additional gravitational participant in a system already filled with moving objects. Once it wandered into the wrong region, it could redistribute some of them. This was especially interesting because scientists were trying to explain evidence for a period of heavy impacts roughly 4 billion years ago. The traditional picture of a distinct late heavy bombardment has become more complicated as lunar science has improved, and researchers continue to debate the exact history and intensity of ancient impacts. That uncertainty matters. Planet 5 was proposed in the context of a particular bombardment problem. If our understanding of that bombardment changes, the requirements placed on any explanation change with it. Science has a habit of doing this. You begin with a mystery. Someone proposes an elegant answer. Better evidence then alters the mystery. The answer must return for another interview. Planet 5 has had several such interviews. Researchers have asked whether an extraplanet could really survive in the proposed region for the required length of time. They have asked whether it could disturb enough material. They have tested different asteroid populations. They have compared the resulting impact histories with what we know about the Moon. Some simulations show that an additional body beyond Mars can indeed survive for very long periods before becoming unstable. Other work has raised problems with using Planet 5 to produce the full bombardment originally envisioned. So we should resist the tempting version of the story in which scientists discovered that a 10th planet definitely existed, caused a catastrophe, and fell into the Sun. That would make a very efficient thumbnail. Reality is more cautious. What we actually have is a plausible dynamical possibility whose role in early solar system history remains uncertain, and uncertainty gives us several questions to carry with us. If Planet 5 existed, how large was it? Exactly where did it orbit? How could its path remain stable for hundreds of millions of years and then suddenly become dangerous? What happened when it began crossing the asteroid belt? Could it really send enough material inward to explain the ancient craters we see? Where did Planet Vesuv go after that? Did it strike another planet? Was it thrown completely out of the solar system, or did its increasingly unstable orbit finally carry it into the Sun? And if the planet vanished so completely, how could we ever distinguish a solar system that once had Planet 5 from one that never did? That final question is perhaps the most important. Anyone can invent a missing world. The challenge is making the missing world useful. A scientific hypothesis must do more than sound possible. It must explain observations. It must survive calculations. It should make predictions or at least produce consequences that can be compared with evidence. And whenever possible, it should do this better than competing explanations. Planet 5 therefore sits in an interesting position. It is close enough to establish planetary dynamics to be taken seriously as a model, but uncertain enough that we cannot casually place it in the solar system's family photograph. It is a possible former member, one for whom we have no photograph, no birth certificate, and no forwarding address. Only gravitational calculations and a collection of ancient clues. There is another reason this story is worth taking slowly. The disappearance of Planet Vesuv, if it happened, reminds us that our current solar system is not a museum exhibit, frozen in its original arrangement. Everything we see is the result of previous events. Mars is small for reasons scientists are still working to understand. The asteroid belt contains only a fraction of the material that once occupied that region. The Moon preserves an impact history that Earth has largely erased through erosion, volcanism, oceans, and plate tectonics. The giant planets have influenced distant populations of icy bodies. Entire classes of objects may have formed in places quite different from where we find them today. When we reconstruct the early solar system, we are not simply rewinding a neat mechanical clock. We are trying to infer a messy history from survivors, and survivors can be misleading. Imagine entering a room after a party has ended. There are 6 chairs around the table. It would be tempting to assume there were always 6 chairs. Then you notice marks on the floor where another chair may have stood. You find a broken leg in the hallway. Someone remembers hearing a crash. Another person insists there were definitely 7 chairs. A third person says the broken leg belonged to a stool. At this point, congratulations, you have invented planetary science. The real investigation involves rather more mathematics, but the principle is similar. The objects that remain contain information about the objects and events that no longer remain. Planet 5 asks us to look at the space between Mars and the asteroid belt and consider whether emptiness itself has a history. Today there is no planet there. That fact is obvious. What is not obvious is whether there was never a planet there. Those are 2 very different statements. For the moment, we do not need to choose between them. We can simply follow the hypothesis and see where it leads. We can give Planet Vesuv its proposed orbit, allow the clock to run, watch the familiar planets circle the young sun, let millions of years pass. Nothing dramatic yet. Another million. Another 10 million. Another 100 million. The additional world remains. Mars continues around the sun inside it. Jupiter moves far beyond the asteroid belt, its enormous gravity influencing the system from a distance. Countless smaller bodies follow their own paths. The solar system seems to be settling down, and if we stopped the simulation there, we might conclude that 5 rocky planets were perfectly capable of sharing the inner solar system. But long-term stability is a demanding thing. A planetary orbit does not need to fail immediately to be unstable. Sometimes gravity works patiently. A tiny change occurs. Then another. Orbital relationships shift. The exoplanet's eccentricity begins to grow. Its safe region becomes less safe. To understand how a planet could disappear from the solar system, we first have to return to a time when there were no planets to disappear. There was no Earth, no Mars, no Jupiter hanging brightly in the night sky. There was not even a night sky, because there was no Earth from which to look at one. About 4.6 billion years ago, the material that would eventually become the Sun, planets, moons, asteroids, comets, and everything else in our solar system was part of a large cloud of gas and dust. Most of that cloud consisted of hydrogen and helium, but mixed through it were tiny grains containing heavier elements produced by earlier generations of stars. Iron, silicon, carbon, oxygen, magnesium, calcium. The basic ingredients were already there, although calling them ingredients makes the situation sound far more organized than it really was. There was no recipe sitting nearby with a helpful instruction saying, add 1 Earth, 4 giant planets, and approximately enough asteroids to worry future astronomers. It was simply material floating through interstellar space. At some point, part of this cloud began collapsing under gravity. Exactly what triggered the collapse is still discussed. A disturbance from a nearby stellar event may have helped compress the material, although gravity itself can cause sufficiently dense regions of molecular clouds to contract. Once contraction began, gravity encouraged more contraction. Material fell inward. As it did, the cloud rotated faster. This is the same basic reason a spinning figure skater turns more rapidly when pulling their arms toward their body, although a collapsing molecular cloud is considerably larger and less likely to win an Olympic medal. The cloud also began flattening. Instead of remaining roughly spherical, much of the material settled into a broad rotating disk surrounding a dense central region. This was the solar nebula, or protoplanetary disk. At its center, more and more material accumulated. Pressure increased, temperature rose. Eventually conditions became extreme enough for nuclear fusion to begin. Hydrogen nuclei combined to form helium, energy was released, and the young sun entered the story. The sun collected the overwhelming majority of the available mass. More than 99% of the mass in today's solar system is contained in the sun, which does make the planets look rather modest when everyone is weighed together. The important material for our purposes was the small fraction that did not fall into the young star. That material remained in the disk. It orbited, it collided, it stuck together, it broke apart, then some of it stuck together again. The first steps toward building planets happened on scales so small that nothing looked remotely planetary. Imagine dust grains moving through a disk of gas. Individual grains can collide gently enough to cling together through electrostatic forces and other surface effects. A grain becomes part of a cluster. Clusters collide with other clusters. Tiny particles gradually become larger aggregates. Those become pebbles. Pebbles become larger concentrations of solid material. The exact route from dust grains to kilometre-scale planetesimals remains an active area of research because growth is not as simple as continuously sticking larger rocks together. Collisions can destroy objects as easily as they build them. Gas produces drag. Different size particles drift at different rates. There are stages at which growth becomes difficult. Planet formation is therefore not quite the peaceful process suggested by children's illustrations, in which small rocks politely gather until a completed planet appears. A great deal of material fails. Some fragments are destroyed. Some spiral toward the young sun. Some are scattered elsewhere. What matters is that enough material manages to assemble into much larger bodies. Once objects become sufficiently massive, gravity begins helping. A larger body can attract nearby material. Its growing mass increases its gravitational influence. Collisions become more frequent. Growth can accelerate. Eventually the disk contains planetesimals, bodies large enough to serve as the major building blocks of future planets. There would have been enormous numbers of them. If we could have watched from a safe distance, the inner solar system would not have contained 4 clean planetary orbits. It would have looked busy. Very busy. Some objects might have been only a few kilometres wide. Others grew to tens or hundreds of kilometres. a smaller number became much larger planetary embryos. These embryos could reach sizes comparable to large moons and, in some models of terrestrial planet formation, eventually approach the mass of Mars. That point is important for Planet 5. The early inner solar system did not necessarily build exactly 4 major rocky objects and then stop because 4 happened to be the number required by a future textbook. It built many competing bodies. The final planets emerged from that population. Earth is a survivor of this process. Venus is another. Mars is another. Mercury is another. But there were almost certainly other substantial bodies that did not survive as separate planets. One of the best-known examples is the hypothetical body usually called Theia. According to the leading giant impact explanation for the Moon's origin, a large protoplanet collided with the young Earth. Material from the impact eventually contributed to the formation of the Moon. Whatever exact details of that event turn out to be correct, the broader lesson is straightforward. The early solar system contained large bodies that are no longer present as independent worlds. Some merged, some collided. Some may have been scattered into the sun. Others could have been thrown outward. Losing a planetary body was not an exception to planet formation. It was part of the process. Location also mattered. The protoplanetary disk was much hotter close to the young sun than it was farther away. In the inner region, materials such as metals and silicate rock could remain solid. Many volatile compounds could not. Farther from the sun, temperatures were low enough for water and other substances to freeze, adding much more solid material from which planetary cores could grow. This helped create the broad distinction we see today. Mercury, Venus, Earth, and Mars became relatively small rocky planets. Jupiter and Saturn became enormous planets rich in hydrogen and helium. Uranus and Neptune developed under still different conditions farther out. But this familiar division was not established instantly. Before the planets reached their final forms, the disk contained overlapping populations of growing objects. Orbits changed. Material moved. Young planets affected nearby planetesimals. And the largest body beyond the forming terrestrial planets was about to become extremely important: Jupiter. Jupiter's enormous mass meant that its gravity influenced a vast region of the developing solar system. Even today, Jupiter can strongly alter the orbits of comets and asteroids. During the formation period, its influence on smaller bodies was even more important because the system contained far more leftover material. Where Jupiter formed, how quickly it formed, and whether it migrated significantly during the solar system's youth are central questions in modern models of planetary formation. The old image of planets forming exactly where we see them today has gradually been replaced by something more dynamic. Planets can migrate. Their interaction with gas can change their orbits. Later, planets can exchange angular momentum with populations of smaller bodies. Large planets can gravitationally scatter one another. This does not mean every proposed migration model is settled fact. Different models are still being tested against the solar system we observe. It does mean that planetary addresses can change. A planet does not receive an orbital postcode at birth and remain there forever. That brings us to the region between Earth and Jupiter. Today it contains Mars and the asteroid belt. Mars is a strange planet in terms of mass. Earth and Venus are broadly comparable in size. Mars is much smaller. Its mass is only about 1/10 that of Earth. For scientists trying to simulate terrestrial planet formation, reproducing this small Mars has historically been difficult. If you begin with a broad disk of solid material extending smoothly through the terrestrial planet region, simulations can sometimes produce a Mars analogue that grows much too large. There is simply too much material available around its orbit. Something appears to have limited the amount of matter Mars could collect. That problem has inspired several ideas about the early distribution and movement of material. One family of models proposes that the disk of rocky building material was truncated or depleted near Mars. Another involves the possible migration of Jupiter, affecting the supply of material in the inner solar system. Whatever the full answer eventually proves to be, Mars tells us that the young solar system did not distribute matter evenly. The asteroid belt tells us much the same thing. If you collected all of the material currently in the asteroid belt and combined it into one body, you would not produce anything remotely comparable to Earth. The present belt contains surprisingly little mass. It is not the shattered remains of an Earth-sized planet that simply exploded, despite an old idea that occasionally returns in popular stories. Instead, it appears to be a heavily depleted population of smaller bodies left from the solar system's formation and later evolution. In the beginning, considerably more material may have occupied this general region. Then gravitational stirring, collisions, resonances, and the influence of planets removed much of it. Some material was sent inward, some outward. Some struck planets, some was thrown from the solar system. The remaining asteroids are survivors. Once again, what we see today is not the original inventory. This is exactly the kind of environment in which the possibility of planet fifth becomes interesting. If large planetary embryos existed throughout the region where the terrestrial planets were forming, could one have remained beyond Mars? There is no immediate reason that every embryo outside Mars had to disappear during the earliest collisions. Planet formation is chaotic enough that different simulations can produce different numbers of final planets. In one outcome, several embryos merge into Earth. In another, an object is scattered into the Sun. In another, a body survives on an orbit that happens to avoid destructive encounters for a surprisingly long period. That last possibility is what we need. Planet Phi does not require the solar system to possess some mysterious new method of making planets. It requires the familiar method to leave one additional survivor. During the later stages of terrestrial planet formation, giant impacts would have dominated the growth of the major rocky worlds. Planetary embryos crossed one another's paths. Close gravitational encounters altered their orbits. Some collided and merged. The inner solar system gradually reduced a complicated population of large bodies into a smaller number of planets. Think of it as a very long elimination process conducted entirely by gravity and collisions. There was no guarantee that 4 terrestrial planets would remain. Run the same starting conditions with tiny differences, and the final arrangement can change. This sensitivity is one of the reasons reconstructing the exact history is difficult. A very small alteration in an object's initial position or velocity can lead, after millions of years of repeated gravitational encounters, to a completely different outcome. One simulated body hits Venus. Another version misses Venus and encounters Earth. Another is scattered outward. Another survives. The laws of gravity are predictable. The long-term result of many interacting bodies can still be chaotic. Eventually, the solar system entered a quieter stage. The gas in the protoplanetary disk did not remain forever. Radiation and winds from the young sun, along with other processes, dispersed much of it within the first several million years. The giant planets had to acquire their large gaseous envelopes while plenty of disk gas remained. The rocky planets could continue assembling for tens of millions of years through collisions between solid bodies. Over time, the enormous population of planetesimals and planetary embryos declined. Some were incorporated into planets, others were ejected, others remained as smaller populations of asteroids and other objects. Earth went through major collisions, Venus grew, Mercury somehow acquired the unusual composition and large iron core that scientists still investigate today. Mars appears to have completed much of its growth relatively early. And beyond Mars, in the scenario we're following, one more body remained, Planet Phi. At first, nothing about its existence would necessarily have seemed temporary. Suppose we could stop the solar system at this moment. The Sun is already recognizable. Jupiter and the other giant planets exist. Earth and Venus have grown into substantial worlds. Mars follows its orbit. The debris population is much smaller than before, and somewhere outside Mars travels another rocky body. It may be smaller than Mars. It may be comparable to a large planetary embryo. Different numerical experiments can use different masses. What matters is that it is large enough for its gravity to affect smaller objects, but not so large that the architecture of the surviving terrestrial planets becomes completely different. Calling it Planet Fifth makes the object sound as though it had a secure official identity. In reality, if such a body existed, there was obviously no distinction between a planet and a planetary embryo written into nature. Those categories are ours. Gravity does not check the International Astronomical Union's definitions before allowing an object to complete an orbit. It was simply a large rocky body orbiting the Sun. From the surface of Mars, if anyone had been there with a telescope and several billion years of patience, Planet 5 could have appeared as another wandering point of light. Depending on orbital geometry and size, its brightness would have changed as the two worlds moved around the Sun. There would have been times when it was relatively close. Other times it would have been far away. Mars would not know it was destined to become the outermost surviving terrestrial planet. Planet Fifths would not know it was supposed to vanish. For an extended period, both could simply continue orbiting. The conditions required for this are more subtle than putting an extra ball around the Sun and hoping for the best. Planetary stability depends on spacing. If two large bodies orbit too close together, repeated encounters can destabilize them quickly. Place them farther apart and the system can survive much longer. But even apparently stable regions can contain resonances. A resonance occurs when orbital periods or other orbital frequencies develop particular mathematical relationships. Repeated gravitational pulls then occur in a coordinated way. Instead of averaging out, the effects can accumulate. A small gravitational nudge repeated at the right intervals can become important. A familiar comparison is pushing someone on a swing. One enormous random push is unnecessary. Small pushes at the correct times can gradually increase the motion. In the solar system, resonances can increase orbital eccentricity or inclination, and can clear certain regions of asteroids. Jupiter produces particularly prominent resonant effects within the asteroid belt. There are gaps in the distribution of main belt asteroids associated with orbital resonances with Jupiter. An asteroid placed in some of those regions can gradually acquire an orbit that becomes much more elongated. It may eventually leave the main belt entirely. The early solar system had these same gravitational principles, but the architecture and populations may have been different. Planet V's proposed home beyond Mars needed to sit in a region stable enough for the planet to avoid immediate destruction. At the same time, it could not be perfectly protected forever. That sounds oddly convenient. A planet that survives exactly long enough to become useful to a bombardment hypothesis and then destabilizes might seem suspicious. This is why numerical experiments matter. Researchers do not simply decide that the orbit should become unstable after a chosen number of years. They assign initial conditions, calculate the gravitational interactions, and see what happens. Many versions fail. The extraplanet may disappear far too early. It may collide with Mars. It may strike another terrestrial planet. It may remain stable for longer than required. Only some arrangements produce the delayed instability that makes Planet 5 interesting. This is not a weakness unique to the idea. Planet formation research often works by generating large numbers of possible histories and asking which ones create a final system resembling the one we actually observe. We have only one solar system to compare against. There is no second identical sun next door where the experiment ran again under controlled conditions. Fortunately, astronomers now observe planetary systems around many other stars, and those systems have taught us something important. Planetary systems come in a remarkable variety of arrangements. There are giant planets extremely close to their stars. There are tightly packed systems containing several planets inside a region smaller than Mercury's orbit. There are planets following highly eccentric paths. There are systems whose architectures look nothing like ours. The neatness of our solar system is only one possible outcome of planet formation. Even here, the apparent neatness is somewhat deceptive. The planets may occupy stable orbits today, but their history includes major changes. Our calm present does not imply a calm beginning. By the time Planet 5 could have settled into its temporary orbit, the worst phase of terrestrial planet building may have passed. The number of large objects had fallen dramatically. major collisions became less frequent. The surviving planets began resembling a recognizable planetary system rather than a construction site. Earth itself was still young and very different from the modern world. Its atmosphere and surface evolved enormously. Impacts continued. Volcanism was intense. The moon was much closer to Earth than it is today. A day on Earth was shorter. The sun was fainter than it is now. There were no forests, animals, oceans filled with fish, or anything else likely to complain about asteroid impacts. Life, if it had begun during part of this early interval, would have been microbial and extremely simple. The moon became particularly important as a record keeper. Earth's crust is active. Plate tectonics recycles enormous areas of surface. Weather erodes terrain. Sediments accumulate. Volcanism covers old landscapes. Oceans alter rocks. Over billions of years, much of Earth's earliest impact record has been erased or transformed. The moon behaves differently. It has no oceans washing away craters, no rain, no active system of plate tectonics comparable to Earth's. Ancient surfaces can survive for extraordinary lengths of time. A large lunar impact can leave a basin that remains recognizable billions of years later. That is why the moon preserves information about the violent period we are trying to understand. It is effectively sitting beside Earth holding records that Earth misplaced. Not perfectly preserved records, admittedly. Lunar geology is complicated. Later impacts overlap earlier ones. Volcanic lava filled some basins. Determining exact ages requires samples, crater counting, remote observations, and careful interpretation. Still, the moon provides one of our best windows into the ancient impact environment of the inner solar system. When scientists studied lunar samples returned by the Apollo missions, many impact-related ages appeared to cluster around roughly 4 billion years ago, especially near 3.9 billion years. This contributed to the idea of a late heavy bombardment, sometimes imagined as a relatively sudden spike in impacts hundreds of millions of years after the planets formed. That picture has been debated and refined. Some of the apparent age clustering may reflect the sampling of material associated with particular large basins. The bombardment may have been more extended. The decline in impacts may have been smoother. Different source populations may have contributed at different times. The exact shape of the impact history remains an important question. But when Planet FIV was proposed, scientists were working with a problem that looked especially intriguing. If the inner solar system experienced a major increase in impacts long after planet formation, should have cleared away much of the nearby debris, what destabilized the impactors? Why would a relatively settled solar system suddenly begin sending large numbers of objects toward Earth and the Moon? Something needed to disturb a reservoir of material. The giant planets offered possibilities. Comets offered possibilities. Asteroids offered possibilities. And then came the idea that perhaps one of the terrestrial planets itself was missing from the story. The extra body beyond Mars would have been born naturally during the same broad process that built the other rocky worlds. It could have survived the violent elimination period. For hundreds of millions of years, its orbit might have remained sufficiently stable. Nothing about its appearance would announce what was coming. It would circle the Sun. Mars would circle inside it. Asteroids would occupy the region farther out. Jupiter would continue applying its distant gravitational influence. One orbit after another would pass without catastrophe. That is where the early history becomes useful. Planet 5 did not need to appear mysteriously at the moment of bombardment. It could have been there all along, a leftover world from the formation process. One additional survivor that had not yet encountered the gravitational combination capable of removing it. And this is where we finally leave the crowded nursery of the solar system and begin looking at Planet FIV itself. The dust has become planets. The giant collisions have removed most of the competing embryos. The gas disk is gone. The basic arrangement is recognizable. Yet between Mars and the asteroid belt there may still be one substantial object that does not appear in any modern diagram. What exactly was Planet 5 supposed to be? The safest answer is that nobody knows what it looked like, because nobody has ever seen it. Planet 5 is a hypothetical object reconstructed from orbital calculations rather than an observed world. We can discuss the range of masses scientists tested, the region where they placed it, the kinds of orbits that allowed it to survive, and the ways it could have affected nearby asteroids. We cannot describe its mountains, atmosphere, colour, moons, or surface with any confidence. That does leave the imagination with rather less furniture to work with, but it also keeps the science tidy. The original Planet 5 experiments explored an additional rocky body positioned between Mars and the inner edge of the asteroid belt. Its starting distance from the Sun was roughly 1.8 to 1.9 astronomical units. Earth, by definition, orbits at an average distance of 1 astronomical unit. Mars averages about 1.52. The main asteroid belt begins farther out, although it is not a sharply defined wall where Mars ends and asteroids suddenly begin. Orbital populations overlap. Resonances create unstable zones, and the inner solar system is much more complicated than a diagram of evenly spaced circles suggests. Planet 5 was therefore placed in a region that looks empty today, but is not physically forbidden territory. That matters. There is a big difference between proposing a planet in a region where orbital mechanics makes long survival virtually impossible, and proposing one in a region where an object can remain for hundreds of millions of years under some starting conditions. Chambers and Lissauer were interested in the second possibility. They tested bodies with masses equal to 1/4 of Mars, 1/2 of Mars, and roughly 1 Mars mass. This already tells us something important about the idea. Planet 5 was not necessarily imagined as another Earth. Even the largest version in those initial experiments was only around the mass of Mars, and many of the more interesting cases involved something considerably smaller. A half Mars mass planet sounds substantial, because it is. It would be vastly larger than any asteroid. It would be massive enough for its gravity to disturb smaller bodies during close encounters. Depending on its composition, it would almost certainly be approximately spherical under its own gravity. It would qualify as a major planetary object by any ordinary understanding of the term. Yet beside Earth, or Venus, it would be modest. Mars itself has only a little more than 1/10 of Earth's mass. Half of Mars gives us a body with only a few % of Earth's mass. Still a planet-sized object, just not the sort of thing likely to dominate the inner solar system. That intermediate size was useful. Make Planet 5 too small, and it becomes less effective at disturbing asteroids. Make it too large, and its gravity starts causing serious problems for the planets that must survive. This is one of the slightly awkward requirements of the hypothesis. Planet 5 must cause trouble. It just cannot cause too much trouble. It has to disturb enough material to matter while leaving Mercury, Venus, Earth, and Mars in recognizable orbits. This is rather like inviting someone to rearrange the furniture without allowing them to move the walls, damage the floor, or accidentally throw the sofa through a window. The allowable range becomes narrower than it first appears. The simulations demonstrated this clearly. When the extra body was as massive as Mars, the planetary system was frequently destabilized in ways that did not resemble the solar system we have today. The extra gravitational influence could cause collisions or losses involving the known terrestrial planets. That is obviously a problem. A model designed to explain ancient impacts cannot solve the problem by removing Earth. Earth is inconveniently necessary for comparing the result with observations. Smaller versions of Planet 5 behaved more gently. A body around half the mass of Mars could, in some simulations, remain on a non-crossing orbit for hundreds of millions of years before becoming unstable. One example began Planet 5 at about 1.9 astronomical units on a nearly circular orbit. For a long time, very little happened. Venus remained Venus. Earth remained Earth. Mars remained Mars. Planet 5 went around the Sun again and again. This uneventful period is essential to understanding the proposal. Popular descriptions of vanished planets naturally focus on the disappearance. because a planet calmly completing several 100 million ordinary orbits is not a particularly efficient way to advertise a video. But most of Planet V's proposed existence may have been exactly that, ordinary. If the object survived for 400 million years before its orbit became dangerous, then it spent an enormous span of time simply being part of the solar system. 400 million years is difficult to appreciate. The entire history of our species occupies only a tiny fraction of that interval. Even complex animal life represents a comparatively recent development in Earth's history. A planet can complete a great deal of uneventful orbiting when nobody is waiting for it to do anything interesting. At one point, 9 astronomical units, one complete revolution around the Sun would take longer than a Martian year. Kepler's laws tell us that planets farther from the Sun generally take longer to complete their orbits. Earth requires 1 year. Mars requires about 687 Earth days. A body near 1.9 astronomical units would take roughly 2.5 Earth years for a single trip around the Sun. Over hundreds of millions of years, that still amounts to well over 100 million circuits. If Planet 5 existed, it was not a temporary visitor passing through for a few afternoons. It could have been an established member of the terrestrial planetary system on any timescale relevant to a human observer. Now, imagine standing on ancient Mars. We will have to ignore the obvious problem that there was nobody available to stand there. Look outward from the Sun at the correct time, and Planet Vigt might appear as a moving point among the stars. Its brightness would depend on its size, surface reflectivity, phase, and distance. Those details are unknown, so there is no scientifically responsible way to tell you that it shone red, white, orange, or a particularly tasteful shade of beige. What we can say is that another sufficiently large rocky world beyond Mars could have been visible from Mars and potentially from Earth if an observer with suitable instruments had somehow existed. From planet Phaia itself, the sky would contain the same major sun and planets that we know, but their positions and brightness would differ. Mars would be the nearest major planet inward. Jupiter would lie outward, beyond the asteroid belt. The Sun would look smaller than it does from Earth, but still overwhelmingly bright. Its light at 1.9 astronomical units would be much weaker than at Earth, because the amount of sunlight received falls with the square of distance. So Planet 5 would receive a little more than 1/4 of the solar energy Earth receives per unit area. That does not tell us its temperature by itself. Atmosphere, albedo, rotation, composition, and many other factors matter. Still, it gives us a broad environmental clue. This would have been a colder location than Earth's orbit. Whether Planet 5 possessed an atmosphere is unknown. Whether it had volcanic activity is unknown. Whether it developed a differentiated interior with a metallic core and rocky mantle would depend on its formation and thermal history. Although planetary bodies of this scale can undergo substantial internal differentiation. Could it have had moons? Possibly. There is no evidence either way. Could water have existed there? Water-bearing minerals and ice were present in early solar system material, so some water content would not be surprising, but we have no specific evidence for Planet Vive. Could it ever have been habitable? There is no useful scientific basis for answering that. Once an object has never been observed and has no known physical remains, inventing oceans and microbial ecosystems begins to tell us more about human enthusiasm than planetary dynamics. The original hypothesis did not need Planet 5 to be interesting geologically. It needed Planet 5 to have mass. It needed an orbit. It needed time. Those 3 things were enough. The gravitational problem becomes easier to understand if we distinguish between an orbit that is stable today and an orbit that is stable forever. When we say a planet is orbiting the Sun, it is tempting to picture a clean ellipse determined only by the gravity of the Sun. If the Sun and Planet 5 were the only 2 objects in existence, the problem would be relatively simple, but they would not have been alone. Mars pulls on Planet Vive, Earth pulls on it, Jupiter pulls on it, Saturn contributes. Even smaller perturbations can matter over sufficiently long periods. Planet 5 pulls back on all of them. Most of these gravitational effects are tiny during any single orbit. Tiny does not mean irrelevant. Suppose a planet receives a small orbital nudge. On the next revolution, the geometry is slightly different. Another interaction occurs. The orientation of the orbit changes, its eccentricity changes, its inclination changes. Some effects cancel, others accumulate. The system develops long-term cycles. A nearly circular orbit can become more elongated. An elongated orbit can bring a planet closer to regions it previously avoided. None of this requires a dramatic collision. Gravity can destabilize an orbit slowly. The original simulations varied Planet V's starting distance and inclination because those differences affected how long the system survived. Starting farther from the Sun generally allowed longer lifetimes in their particular set of calculations. A starting semi-major axis near 1.8 astronomical units produced shorter average survival than one near 1.9 astronomical units. Inclination also mattered. Some moderate inclinations increased longevity. Very high starting inclinations could reduce it again. That is a useful reminder that orbital stability does not depend on one number. You cannot point to 1.9 astronomical units and declare it the official parking space for forgotten planets. Mass matters. Eccentricity matters. Inclination matters. The orbital configuration of the other planets matters. The exact starting phase can matter. Resonances matter enormously. Planetary dynamics is less about finding one safe distance and more about understanding a web of repeating gravitational interactions. The version of Planet 5 that became especially useful to the hypothesis began gently. Its orbit was initially close to circular. That kept it from crossing Mars or entering deeply into the asteroid belt. There were no close encounters with Mars. There was no immediate opportunity to scatter large numbers of asteroids. The planet could therefore remain almost invisible to the later geological record. This solves one part of the timing problem. If Planet 5 is supposed to trigger a later increase in impacts, it cannot spend the previous several 100 million years throwing asteroids toward Earth at the same rate. That would remove the delayed event the model was trying to explain. It needs a quiet phase, then something changes. In the representative simulation described by Chambers and Lissauer, gravitational perturbations gradually increased Planet V's orbital eccentricity. Eccentricity is simply a measure of how stretched an orbit is. An eccentricity of 0 gives a perfect circle. Larger values produce more elongated ellipses. The planets in our solar system have different eccentricities, and their orbits are not exact circles. If Planet V's eccentricity increased, the distance between the planet and the Sun would vary more strongly during each orbit. Its perihelion, the closest point to the Sun, would move inward. Its aphelion, the farthest point, would extend outward. Eventually the orbit could begin crossing territory occupied by Mars on the inner side and asteroids on the outer side. That changes everything. A planet on a separate non-crossing orbit can influence nearby bodies gradually. A planet whose orbit actually enters the same region can experience much closer encounters. Close gravitational encounters are much stronger. An asteroid passing far from planet feels only a modest disturbance. An asteroid passing nearby can have its velocity and direction altered significantly. From the asteroid's point of view, nothing physically touches it. It simply approaches a moving planet, accelerates under the planet's gravity, swings through the encounter, and departs on a different path around the Sun. Depending on the geometry, the asteroid may gain orbital energy or lose it. Its eccentricity can change, its inclination can change, it may enter a resonance, it may become a Mars-crossing object. Eventually some of those altered orbits can become Earth-crossing. Planet 5 therefore does not need to behave like a celestial snowplow, physically pushing rocks inward. Gravity is a This is an important correction to the way asteroid disturbances are sometimes imagined. The asteroid belt is not a dense wall of rubble through which a planet would plough, smashing objects aside every few seconds. The belt is mostly empty space. A planet crossing part of it would spend nearly all of its time nowhere near an asteroid. But over millions of orbits, repeated gravitational encounters with a population of small bodies can still change the distribution substantially. The original test used a comparatively small set of simulated asteroid particles, beginning in the inner belt between about 2.2 and 2.7 astronomical units. At first, unstable particles were removed, and the flow of new Earth-crossing objects decreased. Then, when Planet V's evolving orbit began entering the inner asteroid belt, the number of objects moving onto Earth-crossing orbits rose again. That behaviour was exactly what made the idea attractive. The hypothetical planet provided a delayed trigger. For hundreds of millions of years, a reservoir of asteroids could remain comparatively undisturbed. Then Planet F arrived. Not from another star, not from the outer solar system, from immediately next door. The disturbance came from a planet that had been quietly present all along. But before reaching that stage, the extra world had to avoid several ways of dying too early. Mars was an obvious danger. As Planet V's orbit became eccentric, encounters with Mars became possible. In some simulations, Planet Fudsif collided with Mars. Those outcomes were considered poor matches to the real solar system, because Mars does not display evidence suggesting that it absorbed another large planet hundreds of millions of years after its formation. A collision of that scale would not be subtle. It would release enormous energy and substantially alter the target. Other simulations produced worse outcomes. Known terrestrial planets could become unstable. Mercury might be lost. Mars might be sent into another planet. A full Mars-mass planet fist often created too much disruption. These failures are valuable. When a computer model produces a solar system unlike ours, scientists do not quietly hide the computer under a desk. The failure tells them which initial conditions are less plausible. The observed solar system becomes the filter. Earth must remain approximately where Earth belongs. Venus must survive. Mars must remain small and intact. Mercury must still be present. Planet 5 is the expendable participant. That may sound unfair, but history was clearly not democratic. Only the worlds that remain get names recognized by schoolchildren. The vanished ones, if there were any, receive Roman numerals several billion years later. Another interesting feature of the early calculations was that a half-Mars mass version sometimes survived longer than both smaller and larger versions. That may feel counterintuitive. You might expect the smallest planet always to be least disruptive and therefore longest lived. Orbital dynamics does not always reward simple expectations. Changing the mass changes the way the extraplanet exchanges gravitational influence with the other bodies and how its orbital frequencies evolve. The relationship between mass and survival time is not necessarily monotonic. In the limited set of original experiments, the half-Mars cases produce particularly long characteristic lifetimes. That did not prove the real planet First, if there was one, had half the mass of Mars. 36 simulations cannot uniquely reconstruct a world. They demonstrated that plausible combinations existed. A substantial rocky body could, under certain starting conditions, occupy the region beyond Mars for hundreds of millions of years without immediately destroying the familiar terrestrial system. That is the modest but necessary foundation beneath the larger idea. Now consider what such a world would mean for our mental picture of the early solar system. Today Mars is usually treated as the edge of the terrestrial planet family. Beyond it comes the asteroid belt. That boundary seems natural because we have never known anything else. With Planet 5 included, Mars becomes a middle planet. Earth, Mars, Planet 5, then the asteroid belt. The spacing would still look quite reasonable. Earth to Mars is a larger gap than Earth to Venus. Mars to Planet 5 would add another step before the belt. Nothing in a simple drawing would immediately make the fifth rocky planet look doomed. That is partly why the hypothesis is so effective at challenging our intuition. We tend to assume that the solar system we see is the solar system that had to exist, but orbital mechanics only tells us what configurations are allowed and how they evolve. It does not promise that every original planet survives. There is another subtle point here. If Planet 5 existed for hundreds of millions of years, it may have affected the system even during its quiet period. Its gravitational influence would not have been zero. The exact architecture of Mars-crossing populations, asteroid resonances, and nearby debris could differ from a four-planet system. However, the hypothesis requires these effects to remain modest enough that a large delayed instability is still possible. As the orbit becomes increasingly eccentric, the character of those effects changes. Instead of mild, long-range perturbations, the planet begins approaching small bodies directly. At that stage, Planet 5 changes from an ordinary extraplanet into a mechanism for redistributing the inner asteroid belt, and once the planet is crossing the belt, its own survival becomes increasingly doubtful. The same gravitational chaos that allows it to disturb asteroids also exposes it to stronger resonances and encounters. The planet is not standing safely outside the process, throwing smaller objects toward Earth from a comfortable distance. It is inside the unstable region with them. Each orbit can alter its future. Its inclination may rise. Its eccentricity may rise further. It may spend part of its orbit near Mars and another part among inner belt asteroids. It can approach resonant zones capable of rapidly increasing its orbital instability. In the example that inspired much of the Planet story, the planet eventually entered the powerful secular resonance usually called nu-6. That resonance plays an important role at the inner edge of the present asteroid belt. It is associated mainly with the gravitational influence of Saturn, with the broader planetary system contributing to the relevant precession frequencies. For asteroids, NU6 can strongly increase eccentricity and drive objects onto planet-crossing or even sun-grazing trajectories. A planet encountering that kind of dynamical pathway can also find its orbit altered dramatically. In the simulation, Planet 5 ultimately fell into the Sun. No explosion visible today. No surviving corpse beside Mars. No convenient fragment with a label attached. The Sun simply removed the planet from the inventory. It is an efficient way to erase evidence. A collision with another terrestrial planet would leave a much more obvious geological and compositional problem. Ejection from the solar system is possible for planets under some circumstances, particularly through encounters with giant planets. But Planet 5 began well inside Jupiter, and its specific evolution in the original scenario favoured another ending. Its orbit became increasingly eccentric until the Sun became the destination. For a rocky planet, falling toward the Sun would be a catastrophic process. As the orbit tightened and perihelion decreased, temperatures would rise enormously. The final encounter would destroy the body as an independent planet. Whether it remained largely intact until reaching the Sun, or experienced severe thermal and tidal disruption beforehand, would depend on the exact trajectory and internal properties. The orbital simulations did not need to model every grain of vaporized rock. From the point of view of solar system architecture, once Planet 5 hit the Sun, it was gone, and that gives the hypothesis one of its most convenient features and one of its biggest scientific difficulties. The convenient part is obvious. If a fifth terrestrial planet once existed but later fell into the Sun, we should not expect to find it orbiting beyond Mars today. The model automatically explains the missing planet. The difficulty is also obvious. If the object is completely gone, proving that it was ever there becomes much harder. We cannot send a spacecraft to Planet 5. We cannot measure its rocks. We cannot count its craters. We cannot determine its isotopes. The case must be built indirectly from whether adding such a world solves problems elsewhere. That means the planet itself is not really the evidence. The proposed consequences are: the asteroid belt is evidence to examine. The Moon's impact record is evidence to examine. The ancient surfaces of Mars and Mercury are evidence to examine. The long-term stability of the known planets is evidence to examine. If a model containing Planet 5 produces a better match to those observations than models without it, the hypothesis becomes more interesting. If it fails, then the vanished world becomes unnecessary. And science has very little sentimental attachment to unnecessary planets. This is why we should not become too attached to Planet 5 as a character in the story. It may have existed. It may not have. What matters is whether the physics requires it, permits it, or rules it out. the first question receives a cautious answer. No, current planetary science does not require Planet 5. There are other models for the early impact history and dynamical evolution of the solar system. The second question is more favourable. Under some simulated conditions, an extraterrestrial body beyond Mars can survive for hundreds of millions of years and then become unstable. The third question is where the investigation becomes more interesting, because later work asks whether the specific bombardment produced by such a planet is sufficient, and whether the rest of the solar system survives in the correct state. For now, though, we can give our hypothetical world a basic identity without inventing anything that the calculations do not provide. It was probably envisioned as a small rocky planet or large planetary embryo. Its mass in the original tests ranged from 1/4 of Mars to roughly the mass of Mars, with half-Mars cases providing some of the more promising long-lived examples. It began beyond Mars around 1.8 to 1.9 astronomical units from the Sun. Its orbit was initially low in eccentricity. For a long interval, it did not cross the other terrestrial planets. Its surface, atmosphere, moons, rotation, geology, and appearance remained completely unknown. Then gravitational perturbations slowly changed its orbit. The planet that had spent hundreds of millions of years occupying a relatively quiet lane began drifting dynamically into a much more dangerous configuration. An orbit does not have to change very much before two worlds that never met can begin passing through the same space. For Planet 5, that difference may have taken hundreds of millions of years to develop. At the beginning of the proposed scenario, there was nothing obviously wrong with its orbit. The extra-rocky world moved beyond Mars, somewhere around 1.8 to 1.9 astronomical units from the Sun. Its path was close enough to circular that it did not regularly cross the orbit of Mars, and it remained mostly inside the main asteroid belt. That arrangement could last for a very long time. This is one of the stranger things about orbital instability. We tend to imagine unstable systems as things that immediately look unstable. Put a glass too close to the edge of a table and you can see the problem. Build a tower with one block leaning badly, and everyone nearby understands where this is going. Planetary systems are less considerate. An orbit can appear perfectly respectable for millions of years and still contain the ingredients for trouble later. The reason is that the planets are never moving independently. Every object with mass pulls on every other object with mass. The Sun dominates the motion because it contains almost all of the solar system's mass, but the planets add smaller gravitational effects. Jupiter pulls on Mars, Mars pulls on Earth, Earth pulls on Venus, Saturn pulls on Jupiter. Planet 5, if it existed, would pull on all of them as well. Most of these additional forces are tiny compared with the Sun's gravity. If Jupiter vanished for 1 second and then returned, Earth would not suddenly fly into deep space. The Sun is doing almost all of the work that keeps Earth in orbit. But an orbit lasts longer than 1 second. A lot longer. Planet 5 could complete hundreds of thousands of revolutions around the Sun, then millions, then tens of millions. Each time, the geometry between the planets would be slightly different. Sometimes another planet would be relatively near. Sometimes it would be on the opposite side of the Sun. The gravitational nudges would change in strength and direction. Many would effectively cancel. Some would contribute to slow cycles in Planet Phi's orbit. Over a sufficiently long period, these repeated effects could alter its eccentricity, inclination, and orientation. Eccentricity is especially important here. A planet with a nearly circular orbit stays at roughly the same distance from the Sun throughout its year. Increase the eccentricity, and the orbit becomes more elongated. The average distance may remain similar, but the planet now travels significantly closer to the Sun during one part of the orbit and farther away during another. That sounds like a modest geometrical adjustment. For Planet 5, it was potentially the difference between isolation and close encounters. Imagine 2 circular tracks around a field. One runner stays on the inner track, another stays on the outer track. They can run for as long as they like without colliding. Now stretch the outer track into a long oval. At some point it may begin crossing the inner one. The runners have not changed their basic activity. They are still going around the field. The geometry has changed enough that they can now arrive at the same place. Planet V's problem was similar, except the runners were planets moving several kilometers every second, and the field was approximately the size of the inner solar system. There is another complication. The planets do not simply repeat the exact same ellipse forever. Their orbital ellipses slowly rotate. The orientations of their orbital planes change as well. Astronomers call these gradual changes precession. If you have ever watched a spinning top wobble while its axis slowly traces a circle, you have seen a rough mechanical comparison. Planetary precession is caused by gravitational interactions among the bodies in the solar system. These slow motions introduce frequencies. An orbit can have a characteristic rate at which its perihelion moves. Another planet has its own rate. Asteroids have theirs. When some of those frequencies become related in the right way, a secular resonance can occur. The word secular in astronomy does not mean anything particularly philosophical. It refers to changes that build or cycle over long timescales, rather than repeating simply with each individual orbit. A secular resonance can gradually alter eccentricity or inclination. No collision is required. No planet has to arrive dramatically from the darkness. Gravity simply keeps applying small effects in a coordinated way. The result can become large. This is where the apparent calm around planet Theia becomes deceptive. An object may remain safely separated from Mars for hundreds of millions of years while its orbit slowly evolves. The planet does not wake up one morning and decide that circular motion has become boring. There is no single moment when gravity changes its mind. Instead, long-term interactions shift the orbit until boundaries that once mattered no longer protect it. The original Planet Viv calculations were designed to test exactly this type of delayed instability. The extraplanet needed to last long enough to be useful. If it disappeared 10 million years after the solar system formed, it would simply join the long list of planetary embryos removed during the normal formation process. If it remained perfectly stable for 4.5 billion years, we would presumably still have an additional planet beyond Mars today. Neither result fits the proposed role. Planet 5 had to occupy the awkward middle ground, long-lived but not permanent. In the original work by John Chambers and Jacques Lissoa, many simulated configurations did not manage this. Some exoplanets were lost too early. Others created instability among the known terrestrial planets. A Mars mass version was often too disruptive. Under some starting conditions, however, a smaller Planet 5 could survive for hundreds of millions of years before its orbit became strongly eccentric. This is important because stability is not a simple yes or no property. An orbit that survives for 1 million years is stable for 1 million years. That does not guarantee 10 million. An orbit that survives 100 million years is clearly more durable. That still does not guarantee 1 billion. In chaotic gravitational systems, tiny differences in starting conditions can produce very different long-term histories. Suppose you run one simulation with Planet 5 at a particular point in its orbit. Then you run a second simulation with almost the same setup but move the planet slightly. Not by millions of kilometers, perhaps by an amount that seems irrelevant when compared with the scale of the solar system. After a short interval, the two systems may still look nearly identical. After millions of years, their histories can diverge. One Planet 5 survives, the other encounters Mars. Another simulation sends it toward the asteroid belt sooner. Another keeps it quiet for much longer. This sensitivity is why scientists do not normally rely on one successful computer run and announce that they have reconstructed 4 billion years of history. They test populations of possibilities. They look for patterns. They ask whether the outcome occurs often enough to be plausible, and whether the resulting solar system resembles the real one. For Planet 5, the challenge was particularly severe because 4 familiar planets had to survive the experiment. Mercury could not disappear merely because the simulation found it convenient. Venus could not be thrown into Earth. Mars could not suddenly become 3 times more massive after swallowing the hypothetical planet. The model needed to finish with something close to the system outside your window tonight. That limited the acceptable histories considerably. During its quiet period, Planet Fifth would have spent most of its time far from the other terrestrial planets. Mars was the nearest obvious concern. Mars currently travels on an orbit with an average distance of about 1.52 astronomical units from the Sun. Place Planet 5 near 1.9 astronomical units with a low eccentricity, and there is a comfortable separation. They can repeatedly pass one another in longitude without coming particularly close in physical space. The planets are moving around the same star, but they occupy distinct orbital regions. That is why the fifth world can remain unnoticed by the rest of the story for so long. Its gravity still contributes to the system. Its orbit still precesses. Mars still perturbs it. The giant planets still influence it. Yet there are no repeated close approaches capable of immediately changing everything. Then the eccentricity begins to rise. At first the difference might appear insignificant. Instead of remaining at nearly the same solar distance throughout an orbit, Planet Phi travels a little farther outward and a little farther inward. Mars is still safe. The asteroid belt remains outside. Nothing collides. The eccentricity increases again. The closest point of Planet V's orbit moves closer to Mars. Its farthest point reaches nearer to the inner asteroid population. Now the gravitational environment begins to change. An encounter that was impossible before becomes possible under certain orbital alignments. The planets do not have to collide. A relatively close passage is enough to alter their velocities slightly. When the objects involved are planets, even a small change in velocity can modify an orbit substantially over time. This introduces feedback. Planet 5 develops a more eccentric orbit. The new orbit allows closer encounters. Those encounters can modify the orbit further. The changed orbit can lead to still different encounters. The quiet configuration is starting to lose the property that kept it quiet. Mars becomes especially important at this stage. A close approach to Mars could give Planet 5 a gravitational kick. Depending on the geometry, the extraplanet might gain orbital energy or lose it. Its semi-major axis could change, its eccentricity could increase, its orbital orientation could shift. Mars would also be affected, though Planet V's relatively low mass in the more successful simulations helped prevent the known planet from being altered too severely. You can think of the encounter as a gravitational exchange. The planets approach. Their paths curve because they pull on one another. They separate. Neither orbit is exactly what it was beforehand. There is no need for physical contact. The same principle is used deliberately by spacecraft. Space agencies send probes past planets to perform gravity assists, changing the spacecraft's speed and direction relative to the Sun. Voyager 1 and Voyager 2 famously used planetary encounters to continue through the outer solar system. Planet Phi would not have a navigation team arranging its gravity assists. Its encounters would occur naturally, and unlike a spacecraft, it could return for more. The effect of Mars also helps explain why the instability could accelerate after a long quiet period. Before the orbits approach one another, Mars influenced Planet 5 mainly through distant perturbations. After crossing became possible, close encounters introduced much stronger and less regular changes. The nature of the problem had changed. It was no longer simply a question of gradual secular evolution. Now direct scattering could occur. This is one reason planetary systems can remain calm for an enormous length of time, and then appear to change rapidly. The process that opens the door may be slow. What happens after the door opens can be much faster. Consider an asteroid in the present solar system. It may spend millions or billions of years in the main belt on an orbit that never approaches Earth. Then a slow process moves it into a powerful resonance. Its eccentricity increases. It begins crossing Mars. Planetary encounters alter the orbit further. Eventually it becomes a near-Earth object. To someone watching only the final stage, it may look as though the asteroid suddenly appeared in Earth's neighbourhood. its journey began much earlier. Planet V's proposed evolution works on the same general principle, but with a much larger body. There is also Jupiter to consider. Jupiter sits far beyond Planet V's starting location, but distance does not remove its influence. Jupiter is by far the most massive planet. Its gravity shapes resonances throughout the asteroid belt. Saturn modifies Jupiter's orbital behavior and contributes to the secular architecture of the solar system. Together, the giant planets help create pathways through which asteroid eccentricities can grow dramatically. One of the most important of these pathways is the Nusic's secular resonance near the inner edge of the present main asteroid belt. For low-inclination objects today, it lies near roughly 2.1 astronomical units. The resonance is closely associated with the precession behavior of Saturn and the rest of the planetary system. Objects entering the right dynamical conditions can have their eccentricities increased until they begin crossing Mars or moving farther into the inner solar system. This resonance still matters now. It is one of the important routes by which material can escape the asteroid belt and become part of the near-Earth object population. So when Planet Fifth eventually encountered the Nusics region in the original scenario, it was not entering a fictional trap created specifically for the hypothesis. It was interacting with a real and important feature of solar system dynamics. That does not mean Nusics behaves like a hole in space. There is no visible boundary. A spacecraft would not cross 2.1 astronomical units and suddenly hear an alarm. Resonances are relationships in orbital motion. Their strength and exact location depend on quantities such as semi-major axis, eccentricity, inclination, and the architecture of the planets. The important point is that repeated gravitational effects can accumulate rather than averaging away. For a small asteroid, the result can be a large increase in eccentricity. For a planetary body, the details are more complicated, but the same gravitational structure can contribute to severe instability. Before Planet 5 reached that point, however, its growing eccentricity caused another problem. Its outward excursions approached the inner asteroid belt. This was not merely dangerous for the planet, it was potentially dangerous for Earth. At the beginning of the quiet period, most asteroids in the relevant region could remain on their existing paths. Planet Phi was too far inward to encounter them closely. As its orbit stretched outward, the planet began entering their territory. The difference between the old orbit and the new one might be only a fraction of an astronomical unit. On a solar system diagram, that does not look especially dramatic. For orbital dynamics, it changes which objects can meet. Once Planet 5 enters the asteroid region, every suitable close encounter becomes a possible scattering event. An asteroid can leave with a different eccentricity. Another can be pushed toward Mars. Another may be placed near a resonance. Another may move outward instead. There is no single result. Gravity scatters objects in multiple directions. Only some fraction of the disturbed bodies need to reach Earth-crossing trajectories for the impact rate to rise. The original Planet Fifth proposal depended on a stored population of asteroids remaining available until this delayed disturbance. That point deserves some attention. If all unstable asteroids had already been cleared out during the first 100 million years, Planet Fib would arrive in the belt with very little left to scatter. A person can cause considerable disorder by running through a crowded room. The same person running through an empty room mostly succeeds in looking unusual. The asteroid reservoir therefore matters just as much as the planet. The researchers considered a portion of the inner main belt that could preserve enough bodies before Planet V's instability. Once the planet began crossing that region, close encounters could drive asteroids onto resonances and Mars-crossing paths. Some then evolved into Earth-crossing orbits. The effect was temporary. Planet V was not creating new asteroids. It was destabilizing a population that already existed. As that population was depleted, the supply of new impactors would eventually decline. This is exactly the kind of behavior needed for a pulse or temporary enhancement in impacts rather than a permanently elevated bombardment rate. The timing was the difficult part. Why should planets become unstable around the desired period instead of 100 million years earlier or a billion years later? The answer is not that there was a scheduled event waiting to trigger it at exactly 3.9 billion years ago. The simulation showed that long-lived but finite configurations could exist. Their instability times varied. Some lasted far longer than others. The original hypothesis selected the class of outcomes that happened to match the timescale scientists were trying to explain. That is scientifically legitimate as a test of possibility, but it also means probability becomes important. If the required outcome occurs only under extremely rare initial conditions, the hypothesis becomes less attractive. If it occurs across a reasonable range, it becomes more plausible. This is one of the questions later researchers have examined more critically. There is also a broader issue with the event planet's phi was originally meant to explain. When the idea was proposed, the late heavy bombardment was often discussed as a pronounced spike in the impact rate around 3.9 billion years ago. Our interpretation of the lunar record has become more complicated. Some researchers support a relatively sharp episode. Others favour a bombardment that declined over a longer interval. Sample bias matters because many Apollo rocks may record effects associated with particular enormous impacts. Different crater populations may have had different source regions. Comets, asteroids, and leftover material from terrestrial planet formation may all have contributed. So Planet V's orbital story must now be considered within a bombardment history that is less tidy than it once appeared. That does not make the dynamical question disappear. A fifth rocky planet could still be interesting, even if it was not responsible for one dramatic lunar cataclysm. It simply changes what we would ask the model to explain. Perhaps the most useful part of the Planet V idea is not the claim that this specific planet definitely caused a specific bombardment. It is the demonstration that the early terrestrial system could potentially hide a delayed instability. An additional planetary embryo can survive for a surprisingly long period. The solar system can appear settled while still containing an object whose orbit will eventually cross into a dangerous region. That is not an intuitive result. Human lifetimes train us badly for this. If something remains stable for 10 years, we begin thinking of it as permanent. A house stands for a century and feels old. A mountain remains for millions of years and seems almost eternal. Orbital mechanics works with timescales on which hundreds of millions of quiet years can still qualify as temporary. Planet Fist could have existed longer than many major groups of organisms have existed on Earth. If it vanished around 4 billion years ago, its entire proposed lifetime would still occupy only the earliest part of solar system history. The clock we use matters enormously. During those quiet hundreds of millions of years, no imaginary observer would necessarily have predicted the disappearance from casual observation. You could measure Planet Eve's orbit for decades. It would return as expected. You could measure it for centuries. Still there. A civilization with observations spanning thousands of years might regard the planet as an ordinary permanent member of the solar system. The instability lived in the mathematics of very long-term gravitational evolution. This is one reason modern numerical astronomy can reveal things that ancient skywatching never could. We can calculate millions of years of motion. We can repeat the experiment. We can slightly alter the starting conditions and see where the histories separate. No astronomer needs to personally remain at a telescope until the year 300,000,000-2026. That would create several staffing difficulties. The computer can integrate the equations forward. Even then, long-term predictions have limits, because chaotic behaviour magnifies uncertainty. For Planet Fifth, however, we're not trying to predict a future orbit for an object we observe today. We're testing hypothetical histories. Did configurations exist in which an extraterrestrial planet could remain quiet and later become unstable? Yes. Were all such configurations successful? No. Did some destroy or badly alter the known planets? Yes. Could a smaller extra world survive for hundreds of millions of years before reaching an eccentric, asteroid-crossing orbit? The original experiments found that it could. That gives us the basic mechanism we need. A fifth terrestrial world begins beyond Mars. Its orbit is initially separated from both Mars and the main belt. Long-term gravitational perturbations slowly modify that orbit. The eccentricity grows. The planet begins approaching Mars. Close encounters become possible. Its semi-major axis and orbital shape can change further. The outer part of the orbit extends into territory occupied by asteroids. From that moment, Planet 5 is no longer simply experiencing instability. It is passing instability onto smaller bodies. A planetary mass body repeatedly moving through the inner asteroid belt would not need to hit many asteroids to cause trouble. It would only need to pass close enough for gravity to change their orbits. That distinction is important, because the asteroid belt is not the crowded field of tumbling rocks that science fiction sometimes gives us. If you flew through it, you would probably see very little. The distances between large asteroids are enormous. Spacecraft have crossed the belt many times without having to perform frantic last-second maneuvers around boulders. Planet Phi could therefore enter the asteroid belt and complete orbit after orbit without resembling a wrecking ball smashing through a wall. Most of the time, absolutely nothing would be nearby. Then, occasionally an asteroid would pass close enough for the planet's gravity to matter. That was enough. Imagine one of the smaller bodies following a fairly ordinary orbit around the Sun. For millions of years, it travels through approximately the same region. It may experience gradual perturbations from Jupiter, Saturn, Mars, and the other planets, but it remains part of the asteroid population. Planet 5 approaches, not directly enough for a collision, just close enough. As the asteroid falls toward the planet, it accelerates. Its path curves. Then it swings past and escapes again. The encounter may last only a short time. Afterward, the asteroid is still orbiting the Sun, but it is not necessarily following the same orbit. Its speed may have changed slightly. Its direction may have changed. Its eccentricity can increase or decrease. Its inclination can shift. Its closest approach to the Sun may move inward. Its farthest distance may move outward. A body that had spent hundreds of millions of years behaving like an ordinary main belt asteroid can leave a single encounter on a path that eventually carries it toward Mars. This type of gravitational scattering happens throughout planetary systems. Jupiter does it extremely well because Jupiter is enormous. The giant planet has thrown countless smaller objects onto new trajectories during solar system history. It has also captured some temporarily redirected comets and contributed to sending other objects completely out of the solar system. Planet 5 would have been a much weaker gravitational scatterer, but it had one considerable advantage. It was right there. Once its eccentric orbit entered the inner asteroid belt, it could repeatedly encounter objects in a population that had previously been relatively protected. The word repeatedly matters. One pass through the belt would accomplish very little. 10 passes might still accomplish very little. But Planet 5 was orbiting the Sun approximately once every few years. Give it 1 million years in an asteroid crossing configuration, and there are hundreds of thousands of opportunities for its orbit to pass through that region. Give it 10 million years, and the number becomes much larger. The planet does not have to meet every asteroid. It only needs to encounter enough of them. The original Planet 5 calculations were designed to see whether this process could create a renewed supply of bodies moving toward Earth and the Moon. Before the planet entered the belt, the number of easily destabilized asteroids could gradually decline. Bodies already sitting on unstable orbits would be removed relatively quickly. Some would strike planets, some would hit the Sun, others would be scattered elsewhere. After a long enough interval, the remaining population would be dominated by objects whose orbits were comparatively durable. This creates a problem if you're trying to explain a later burst of impacts. You need some way of reaching objects that survive the initial clearing. Planet Phi provided that possibility. Instead of waiting for those asteroids to become unstable by themselves, an additional planet could enter their neighbourhood and modify their orbits directly. It was effectively opening a new route out of the belt. not every asteroid would head inward. Gravity does not contain a setting marked send to Earth. Some objects could be pushed outward. Some could acquire larger inclinations. Some might eventually collide with planet Earth itself. Others could continue on altered but harmless orbits. A relatively small fraction would enter trajectories that brought them toward the terrestrial planets. For Earth and the Moon, a small fraction could still be an enormous number. The early asteroid belt contained considerably more material than it does today. The present belt has a total mass far smaller than Earth's moon, and it represents a population that has been depleted over billions of years. If Planet 5 encountered an earlier, more heavily populated belt, there would be more objects available to scatter. That does not mean the region was packed tightly with rocks. It means the statistical chance of meaningful encounters over millions of years would have been greater. One of the most important effects would be moving asteroids toward resonances. A close encounter does not have to transform an asteroid directly into an Earth-crossing object. It can simply move the asteroid into the wrong orbital neighbourhood. After that, the larger architecture of the solar system takes over. Jupiter is especially good at creating these neighbourhoods. Asteroids in the main belt orbit the Sun at different rates depending on their distance. Some locations produce simple relationships between an asteroid's orbital period and Jupiter's. An asteroid in the 3-to-1 mean motion resonance, for example, completes roughly 3 orbits for every one completed by Jupiter. That sounds orderly. In practice, repeated gravitational influences can make the asteroid's orbit increasingly eccentric. The present asteroid belt contains visible gaps at several of these resonant locations known as Kirkwood gaps. They are not empty because Jupiter physically collected the asteroids. They are depleted because long-term orbital dynamics makes those regions difficult places in which to remain. There are also secular resonances such as Nu 6, where the slow precession of an asteroid's orbit interacts with characteristic frequencies of the planetary system. For objects near the inner edge of the main belt, Nu 6 can increase eccentricity until the asteroid begins crossing the orbit of Mars. From there, additional encounters can bring it farther inward. This is not merely something that may have happened billions of years ago. It is still happening. The modern near-Earth asteroid population is continually supplied by objects escaping from the main belt through resonances and other dynamical pathways. An asteroid can spend most of its existence far from Earth, drift into a resonance, become increasingly eccentric, and eventually appear in the inner solar system. By the time we discover it as a near-Earth object, the important part of its journey may have begun millions of years earlier. Planet Fifth would have accelerated this process for some ancient asteroids by placing them onto those escape routes. It was not necessarily delivering every impact personally. That would have required a rather unreasonable level of service from one small planet. It only had to disturb the reservoir. Once an asteroid reached a Mars-crossing orbit, Mars became another participant. A close passage by Mars could alter the orbit again. Eventually, Earth and Venus could become accessible. Some objects would approach the Sun closely enough to be destroyed or absorbed. Others might survive on planet-crossing paths for millions of years. A few would strike something. When a kilometre-scale asteroid hits a planet at many kilometres per second, something notices. The energy involved is enormous. Even a relatively small asteroid can excavate a crater far larger than itself. Larger bodies can create basins hundreds of kilometres across. On Earth, geological activity removes or hides much of that ancient record. On the Moon, the scars remain much easier to see. This is why a disturbance beginning beyond Mars can become relevant to lunar geology. The Moon never needed to encounter Planet Viv. Earth never needed to encounter Planet Viv. The missing planet could remain millions of kilometres away, while indirectly increasing the number of smaller bodies arriving in the inner solar system. It is a chain of events. Planet 5 enters asteroid crossing territory. An asteroid receives a gravitational kick. Its orbit changes. A resonance increases the change. Mars becomes reachable. Another encounter occurs. The asteroid moves inward. Eventually its path intersects Earth or the Moon at the wrong moment. Nothing in that sequence requires the asteroid to know where it is going. orbital evolution simply increases the range of places where it can be. The impact happens when two objects occupy the same location at the same time. Usually they do not. Occasionally they do. With enough asteroids, occasionally becomes important. The original simulations used test particles to represent asteroids. A test particle has an orbit and responds to the gravity of the planets, but its own mass is treated as negligible. That allows researchers to follow many small objects without making the calculation unnecessarily expensive. Planet Fisk could perturb the particles. Jupiter could perturb them. Mars could perturb them. The particles did not significantly alter the planets in return. This is a reasonable approximation when comparing a planet with ordinary asteroids. A large asteroid has mass, of course, but its gravitational effect on something the size of Mars is so small that ignoring it makes the problem far easier without ruining the basic dynamics. The simulated asteroids began in a portion of the inner main belt. During the earlier quiet period, some unstable objects escaped naturally. The supply of new Earth crossers declined. Then, Planet V's orbit expanded into the asteroid region. The number of bodies being moved onto Earth-crossing trajectories increased again. This was the central attraction of the model. You could produce a delayed release of impactors without requiring the entire asteroid belt to become unstable immediately after the planets formed. A reservoir survives. A planet becomes unstable later. The planet taps the reservoir. The inner planets receive the consequences. There was another useful feature. Planet Fire would eventually disappear. If the extra planet had remained on its asteroid-crossing orbit indefinitely, the disturbance could continue too long. It might clear too much of the belt. It could eventually disrupt Mars or another terrestrial planet, and, most obviously, we would still need to explain why it is missing now. Its own instability provided an end to the process. As Planet V's orbit became more extreme, it entered regions where powerful gravitational resonances affected it as well. In the original example, the planet was ultimately driven into the Sun. That removed the scatterer. Asteroids that had already been destabilized continued evolving on their new orbits, but no Planet 5 remained to keep disturbing the reservoir indefinitely. The bombardment produced by the mechanism would therefore have a rise and a decline. At least that was the goal. The exact shape of that rise and decline is where the hypothesis becomes more difficult. An elegant mechanism is not automatically a successful one. Scientists have to compare how many asteroids are delivered, how quickly they arrive, how long the enhanced impact rate lasts, and what happens to the rest of the asteroid belt. If the Moon's craters require 100 times more material than the mechanism can provide, the fact that the mechanism works in principle is not enough. If Planet Fifth sends the correct number of objects inward, but leaves the asteroid belt looking completely unlike the one we observe, that is also a problem. If it produces the right bombardment but destroys Mars in half the simulations, enthusiasm becomes understandably limited. Planetary dynamics is full of this sort of negotiation. A model is asked to explain one mystery without creating three new ones. For Planet 5, one question concerns the amount of material available in the particular portion of the asteroid belt it could reach. The planet did not initially plunge through the entire main belt from its inner edge all the way to Jupiter. Its orbit first interacted with the inner region. That region must contain enough mass to provide the required impactors. If the reservoir is too small, Planet V can scatter it very efficiently and still fail to produce enough lunar impacts. Later studies examined this issue more closely and found that reproducing a very large, sharp, late-heavy bombardment using the Planet V mechanism could require more material in the relevant asteroid population than appears plausible. That does not make the underlying orbital behavior impossible. It challenges the scale of the claimed consequence. There is an important difference between saying, an unstable Planet 5 could send asteroids into the inner solar system, and saying, Planet 5 caused the entire lunar bombardment. The first statement concerns dynamics. The second requires the numbers to work. Science becomes especially interesting in the space between those two statements. The idea may be physically possible without being the dominant explanation. It may contribute without being responsible for everything. or it may eventually prove unnecessary. When Planet Phi was first proposed, the late heavy bombardment was often presented as a dramatic increase in impacts around 3.9 billion years ago. Since then, interpretations of the lunar impact record have changed. Researchers have questioned whether there was one sudden spike at all. Some evidence can be consistent with a prolonged decline in bombardment following planet formation, possibly with large individual impact events superimposed on that decline. Other dynamical models have been developed involving the migration and instability of the giant planets. The precise timing of giant planet migration has itself been revised and debated. There is no single uncomplicated movie of the early solar system sitting in a laboratory drawer. What we have are observations, samples, crater counts, isotope measurements, orbital calculations, and competing models that try to make those pieces fit. Planet Phi remains interesting because it demonstrates how a delayed disturbance could arise in the terrestrial region without requiring a new object suddenly to arrive from somewhere else. The planet is already present. The delay comes from orbital evolution. Once the orbit changes, a region that had been dynamically separate becomes accessible. That is a powerful general idea in planetary science. Small changes in orbital boundaries can expose completely new populations to gravitational scattering. It happens with comets. It happens with asteroids. It happens during planet migration. If giant planets shift their orbits, resonances shift with them. A stable population can suddenly find itself sitting in an unstable zone without moving anywhere first. The gravitational architecture moves around it. Planet Phi offers the reverse version. Instead of a resonance sweeping across the asteroid population, the planet itself wanders into the population. There is no intention behind the word wander. Planet Phi would follow the equations of motion as strictly as any other body. But from our perspective, its trajectory would appear to drift from a relatively isolated orbit into territory filled with smaller objects. The change might take millions of years. Once underway, however, the consequences could spread rapidly by geological standards. Suppose an asteroid is kicked directly into N6. Modern dynamical studies show that objects entering this resonance can reach Earth-crossing trajectories on timescales of roughly 1 million years or less. That is not immediate to us. If someone tells you an asteroid will arrive in 500,000 years, there is probably no need to cancel dinner. On the scale of a 4.5 billion-year-old solar system, it is quick. Planet 5 could disturb an object, and within a tiny fraction of solar system history that object might be moving through Earth's neighbourhood. Many would never strike Earth. Near-Earth space is still mostly empty. The Moon is smaller still. Most potential impactors eventually meet other fates. Some hit the Sun. Some strike another planet. Some are ejected after planetary encounters. Others survive until another perturbation changes their orbit again. The impact record is produced by the unlucky minority, but the Moon has had billions of years to collect unlucky minorities. Every crater represents one intersection between two trajectories. Every large basin represents an especially energetic one. Now imagine increasing the number of bodies placed onto those crossing trajectories. The chance of impacts rises. Earth and the Moon sweep through space along their orbits over and over again. An individual asteroid can cross Earth's orbital distance many times without hitting anything. Eventually it may be removed by another process, or eventually Earth arrives at the crossing point at the wrong moment. Mars experiences the same problem. Mercury does too. Venus cannot opt out. The entire terrestrial region shares the enhanced population. That means a genuine planet Phi-driven bombardment should not be thought of as something aimed specifically at the Moon. The Moon is simply where we preserve some of the clearest ancient evidence. Mars should receive impacts. Mercury should receive impacts. Earth should receive impacts, although Earth later hides much of the damage. Even Planet 5 itself could be struck. A world responsible for scattering impactors is not granted immunity from them. The growing population of planet-crossing asteroids would make the inner solar system a more hazardous place for everyone. How hazardous depends on the amount of material. This brings us back to the ancient asteroid belt. The present belt is not a pristine sample of its original population. Collisions have shattered bodies. Resonances have removed objects. Planetary migration may have depleted and rearranged populations. Some asteroids may even have formed in regions different from where we find them now. The belt contains multiple compositional groups reflecting a complicated formation and transport history. Trying to reconstruct its state 4 billion years ago is therefore difficult. You cannot simply count today's asteroids and multiply backward. Some families are products of later collisions, some original bodies are gone, others migrated into or out of particular regions. A hypothetical Planet 5 adds another depletion mechanism that must be included in the reconstruction. This creates a useful test. If Planet 5 spent millions of years disturbing the inner belt, the resulting distribution of surviving asteroids should not be arbitrary. The survivors carry a dynamical record. Their eccentricities and inclinations matter. Which regions are populated matters. Which resonances are empty matters. A successful model should finish not only with the correct planets, but with an asteroid belt at least broadly compatible with what exists today. That requirement makes the problem much harder than simply showing that a planet can throw rocks toward Earth. Throwing rocks is easy. Leaving the right rocks behind is difficult. Planet 5 also has to avoid becoming too efficient. If it clears essentially the entire inner belt, we have to explain why asteroids remain there now. If it barely disturbs anything, it cannot produce a meaningful impact enhancement. The planet needs another balancing act. Enough instability to matter, not enough to erase the evidence completely. The more conditions we add, the more specific the acceptable histories become. Yet the basic process remains easy to understand. A fifth terrestrial planet starts on a relatively calm orbit beyond Mars. Its eccentricity grows. The orbit begins crossing Mars. Further perturbations extend the path outward. Planet 5 reaches the inner asteroid belt. Close encounters scatter asteroids. Some are moved toward powerful resonances. Those resonances increase eccentricity. Mars-crossing objects appear. A fraction evolves into Earth-crossing orbits. Impacts become more frequent. Planet Vif itself continues becoming less stable. Eventually it is removed. The scattered population then decays as impactors hit planets, fall into the Sun, or are otherwise lost. If that sequence occurred, the result would not look dramatic from one moment to the next. There would be no single evening when the sky suddenly filled with asteroids. Even during a period described as heavy bombardment, impacts large enough to produce major craters could still be separated by enormous amounts of time on a human scale. Millions of years can contain many catastrophes while still being mostly quiet on any particular Tuesday. This is useful to remember whenever we hear phrases such as asteroid storm or cosmic bombardment. The geological record compresses time. A map showing dozens of ancient lunar basins places events separated by millions of years beside one another. To us, they look simultaneous because 4 billion years of history have been flattened into one image. The moon experienced them one at a time. An enormous object struck. The surface melted and fractured. Ejecta spread across the surrounding landscape. Then there could be a long period of relative quiet. Another object arrived later. Another basin formed. Smaller impacts continued between them. Over enough time, the surface accumulated the record we see. If Planet Fifth contributed to that record, its fingerprints would therefore be statistical rather than obvious. There would not be one crater marked as the moment Planet Fifth entered the belt. We would look for an increase in the delivery rate of impactors with the kinds of sizes and compositions expected from the inner asteroid population. We would compare crater ages. We would compare lunar samples. We would examine whether Mars and Mercury record a similar period. We would ask whether the inferred impactors look more like asteroids or comets, and we would calculate whether the number of bodies Planet Fifth could realistically scatter was enough. That last question takes us away from the orbit of the missing planet and toward the damaged worlds closer to the Sun, because the reason anyone cared about sending all these asteroids inward was not simply that the orbital mechanics were interesting. The inner solar system contains surfaces that appear to remember an exceptionally violent youth. The Moon carries enormous basins. There are craters everywhere. Small ones sit inside larger ones. Larger ones overlap older basins. Some impact structures are so enormous that they cover substantial portions of the lunar surface. From Earth, many of the dark areas we can see with the unaided eye are broad volcanic plains that later filled enormous impact basins. The Moon did not begin with this appearance. Its surface accumulated damage over billions of years, and the oldest terrain preserves evidence of a period when large impacts were much more common than they are today. That much is not controversial. The difficult question is exactly how the bombardment happened. For decades, one influential idea held that something dramatic occurred around 3.9 billion years ago. According to this picture, the rate of major impacts increased sharply several hundred million years after the planets had formed, producing a relatively brief period of intense collisions known as the Late Heavy Bombardment. Sometimes it was called the Lunar Cataclysm. The name makes it sound like the Moon spent several million years hiding under a table, which would have been understandable. The original evidence came largely from rocks returned by the Apollo astronauts. When scientists measured the ages of minerals affected by impacts, many of the dates appear to cluster around the same general period, close to 3.9 billion years ago. Impact dating works because a sufficiently violent collision does more than make a hole. An asteroid or comet arrives at many kilometers per second. Its kinetic energy is converted almost instantly into heat, pressure, excavation, fracturing, and motion. Rock can melt, some can vaporize. Material is thrown outward over enormous distances. A large impact can create a basin hundreds or even thousands of kilometers across and produce a layer of impact melt that later cools and solidifies. Certain radioactive isotope systems inside those rocks can record when the material was heated or recrystallized. By measuring those systems carefully, scientists can estimate when the impact occurred. Apollo samples produced a curious pattern. Many impact-related ages fell within a comparatively narrow interval, around 4 billion years ago. If those samples represented separate major collisions across the Moon, the implication was striking. Perhaps the impact rate had not simply declined smoothly after the planets formed. Perhaps it had risen again. That created a major problem for solar system history. The earliest period of planet formation was naturally violent. There were planetary embryos everywhere. Planetesimals remained on crossing orbits. Large collisions were part of the normal process of assembling the planets. You would expect intense bombardment then, but after hundreds of millions of years, much of that leftover material should have been removed. Objects on unstable orbits tend not to remain unstable forever. Eventually, they hit something, fall into the sun, or are scattered elsewhere. So if the Moon experienced another major pulse of impacts much later, scientists needed a mechanism capable of destabilizing a new reservoir of objects. That is precisely the kind of problem Planet Theus was designed to address. The extraplanet could remain relatively quiet beyond Mars while the early bombardment declined. Then its orbit could become unstable. It could enter the inner asteroid belt. A new population of asteroids could be scattered toward the terrestrial planets. The timing seemed appealing. A planet left over from formation could act as the delayed trigger. But the Moon is not a perfect historical archive. It preserves ancient surfaces far better than Earth, but reading those surfaces is still difficult. The Apollo missions landed at only a handful of locations, all on the near side of the Moon and within a relatively limited geographical region. The returned samples are extraordinary. They transformed planetary science. They are also not a random collection gathered evenly across the entire Moon. This matters because one enormous impact can spread debris over huge distances. The Imbrium Basin is a good example. It is one of the largest and most obvious impact structures on the near side. The basin formed when a large object struck the Moon roughly 3.9 billion years ago. The impact blasted material across a vast portion of the lunar surface. Some rocks collected far from the basin may contain material affected by Imbrium. If several Apollo samples all record the same enormous event, then a cluster of ages near 3.9 billion years does not necessarily prove that many unrelated giant impacts happened at exactly that time. It might partly reflect one particularly energetic impact contaminating multiple sample locations. This is one reason the simple version of the late heavy bombardment has become less secure. There is still strong evidence that the early Moon experienced an intense period of basin-forming impacts. What researchers debate is whether there was a sudden, narrow spike around 3.9 billion years ago, or a more extended sequence of heavy impacts stretching across a much longer interval. That distinction matters enormously for Planet 5. If there was one sharp cataclysm, a successful model must explain why so many impactors suddenly arrived together. If bombardment instead declined gradually over several 100 million years, the requirement changes. You may not need a single dramatic trigger at all. The Moon also contains basins older than the classic 3.9 billion year interval. Evidence from lunar samples and remote observations suggests that large impacts were happening before then. Some studies have identified impact ages around 4.2 billion years ago. More recently, material returned from regions on the lunar far side has strengthened the case that basin formation extended well outside a narrow 3.8 to 4.0 billion year window. That does not erase the later large impacts. Imbrium happened, Oriental happened, Nectaris happened. Many other major basins formed. The question is how those events were distributed through time. For the moment, imagine the inner solar system around 4 billion years ago, without insisting on one precise bombardment curve. The Moon is already heavily scarred. Earth is being struck as well. Mars and Mercury are collecting their own craters. Venus is receiving impacts even though much of its ancient surface record will later be erased by geological activity. Asteroids moving inward from the belt enter planet-crossing orbits. Some survive for millions of years without hitting anything. Others are removed quickly. Every orbit creates another opportunity for an encounter. The Earth presents a larger target than the Moon. It also has stronger gravity. An asteroid approaching Earth can be gravitationally focused toward the planet, increasing the effective collision probability. The Moon receives fewer impacts simply because it is smaller and less massive. Still, it preserves those impacts much better. Earth is terrible at keeping old craters. Its atmosphere destroys many small incoming objects before they reach the ground. Weather erodes impact structures. Rivers cut through them. Sediments bury them. Volcanoes cover them. Oceans conceal enormous portions of the crust. Plate tectonics eventually recycles old surface material into the mantle. The earliest Earth has been extensively rewritten. If Earth had remained geologically quiet like the Moon, our planet might display an ancient crater record impressive enough to make the lunar highlands look almost tidy. A large impact into early Earth would have produced consequences far beyond a crater. An object tens of kilometers across could release energy on a scale difficult to appreciate. Rock near the impact site would melt. Some would vaporize. An enormous plume of debris could enter the atmosphere. Material could be thrown around the planet. The atmosphere would heat. If the impact occurred in an ocean, huge quantities of water vapor could enter the air. Very large impacts could temporarily alter climate and surface conditions over broad regions. During the earliest period, when the impactors were larger and more frequent, some collisions may have affected the entire planet. This has led naturally to questions about early life. If life had already begun on Earth during heavy bombardment, could repeated giant impacts sterilize the planet? The answer appears to depend heavily on the size and frequency of the impactors. A truly enormous collision can devastate the surface. That does not necessarily mean every living organism dies. Microbial life could survive underground, beneath the seafloor, or in regions protected from the worst effects. Some models suggest that impacts capable of completely sterilizing Earth would need to be extraordinarily large. The bombardment could therefore be destructive without repeatedly resetting biology to zero. It might also create useful environments. Impact-heated hydrothermal systems can circulate hot water through fractured rock. Those systems can persist after the immediate violence has ended. Minerals, heat, liquid water, and chemical gradients can produce environments of interest to origin of life researchers. So impacts are not simply cosmic erasers. They alter environments in complicated ways. The timing becomes especially interesting because some of the oldest evidence related to early life appears not enormously younger than the period of intense bombardment. Exactly when life began remains uncertain. The oldest proposed biosignatures are debated, but life seems to have emerged surprisingly early in Earth's history. That means whatever was happening in the sky, biology eventually managed to continue beneath it. Mars was undergoing its own version of the same bombardment. Unlike Earth, Mars preserves vast ancient surfaces. The southern highlands are densely cratered. Huge impact basins such as Hellas and Argia record collisions involving large objects early in Martian history. The northern hemisphere is very different, with lower terrain and fewer visible ancient craters across broad regions. Mars also preserves evidence that liquid water once flowed across its surface. Valley networks, minerals formed in water, ancient lake deposits, and other features show that the early Martian environment was not simply the cold, dry desert we see today. Large impacts during this period could have affected the atmosphere and climate. A collision can heat the atmosphere. It can melt ice. It can release water vapor and other gases. For a short interval, an impact may create local or even regional conditions very different from the normal climate. At the same time, repeated enormous impacts can erode an atmosphere. Again, there is no simple rule that impacts either help or harm a planet. They do both, depending on size, location, frequency, atmospheric conditions, and timing. Mercury presents an even more heavily cratered landscape. Its enormous Caloris basin, about 1,550 kilometers across, was created by one of the largest impacts preserved on the planet. The collision was so powerful that effects appear on the opposite side of Mercury as well. The impact excavated vast amounts of crust. Later volcanic material filled parts of the basin. Elsewhere, ancient cratered terrain records the same general era of violence seen across the terrestrial solar system. Mercury's position close to the Sun did not protect it. If anything, its neighbourhood was crossed by objects moving at very high velocities. Venus is more frustrating. Venus is approximately Earth's size and would have received its share of early impacts, but its present surface is geologically much younger than the oldest terrains on the Moon, Mercury, or Mars. Extensive volcanic and tectonic activity erased much of the ancient record. We know the collisions must have happened because Venus occupied the same inner solar system filled with impactors. We simply cannot reconstruct the earliest cratering history from its present surface with the same confidence. That leaves the Moon carrying much of the burden. And the Moon has one other advantage. We have pieces of it in laboratories. Apollo astronauts returned hundreds of kilograms of lunar material. The Soviet lunar missions returned smaller, but extremely valuable samples. Lunar meteorites arrive naturally on Earth after impacts blast rocks away from the Moon. More recent sample return missions have added material from new locations. Each sample can potentially help separate local events from global ones. This is especially important because the original late heavy bombardment idea was built from a limited sample geography. Ages from the lunar far side or from basins far away from Apollo landing sites can test whether the 3.9 billion year cluster appears everywhere. If it does, a system-wide event becomes more convincing. If older basin ages become common, then the idea of one narrow cataclysm weakens. Recent results have continued pushing the story toward a more complicated impact history. Evidence for events around 4.2 billion years ago suggests that major basin formation began well before the classic 3.9 billion year period. Samples associated with the enormous South Pole Aitken region and younger basins on the far side are especially important because they come from places completely different from the Apollo sampling area. The South Pole Aitken Basin itself is one of the largest impact structures in the entire solar system. It spans roughly 2,500 kilometers across the lunar far side. It is so large that a collision capable of creating it excavated deeply into the Moon. Determining its exact age would give scientists a crucial anchor for the early impact chronology. Unfortunately, dating a basin that old is difficult. Later impacts mix material. Ejecta from different events overlap. Rocks are broken, buried, heated again, and redistributed. The Moon keeps a better diary than Earth, but someone has spilled several billion years of gravel across the pages. Planet Firth enters this debate because its original purpose depended on delayed timing. The model was attractive when there appeared to be a clear late pulse of impacts requiring a trigger. If bombardment was instead prolonged, the need for Planet 5 becomes less obvious. But that does not immediately eliminate it. A wandering Planet 5 could still contribute a later population of impactors, even if it did not create the entire bombardment. The question becomes quantitative. How many asteroids can it deliver? Over what time scale? What sizes are they? Which part of the asteroid belt do they come from? Do those bodies produce a crater distribution matching the Moon? Does the mechanism also fit Mars and Mercury? And what happens to the asteroid belt afterward? These questions are much more demanding than simply showing that a fifth planet can scatter a few test particles. Suppose Planet 5 destabilizes 10,000 asteroids. That sounds impressive until you ask how large they are. 10,000 objects 100 meters across produce a very different geological record from 10,000 objects 10 kilometers across. Large lunar basins require enormous impactors. You cannot build Imbrium by throwing pebbles at the Moon very enthusiastically. The size distribution of the impactor population therefore matters. Researchers can estimate the size of a projectile required to create a crater of a given diameter, although the result depends on impact velocity, impact angle, target material gravity, and other factors. From crater populations, scientists can then infer something about the objects that produce them. This gives another possible clue to the source. Different reservoirs of asteroids and comets can have different size distributions and compositions. If the lunar craters resemble those expected from main belt asteroids, an asteroid source becomes more attractive. If they require a very different population, a planet far through mechanism based on disturbing the inner asteroid belt becomes harder to defend. There has been considerable debate over exactly what the ancient lunar impactors looked like. Some studies found similarities between lunar crater size distributions and the modern main asteroid belt. Other work suggested that the populations may not match so simply. The oldest craters may record leftover planetesimals from terrestrial planet formation rather than asteroids destabilized much later. Different periods may involve different sources. That possibility makes sense. There is no requirement that every crater on the Moon came from the same reservoir. During the earlier stages, leftover planetary embryos and planetesimals would dominate. Later, destabilized asteroids might contribute. Comets could arrive during episodes of giant planet migration. The relative importance of each group could change with time. A real bombardment history may therefore resemble several overlapping declines and pulses, rather than one single event. That is much less convenient for naming purposes. The late heavy bombardment, plus several other things happening at different rates would have been difficult to fit on conference badges. The giant planets provide one of the major competing explanations. Models of early solar system evolution show that Jupiter, Saturn, Uranus, and Neptune may have changed their orbital configuration substantially after formation. If the giant planets migrated or experienced an instability, their resonances would shift. Asteroids and icy bodies that had occupied stable regions could suddenly become unstable. Large numbers could then be scattered throughout the solar system. This became especially influential through versions of what is known as the Nice model, named after the city of Nice in France, where some of the researchers worked. It is pronounced like the city, although the model's consequences for nearby asteroids were not particularly nice. Early versions of the model placed the giant planet instability hundreds of millions of years after solar system formation. That timing provided a natural trigger for a late heavy bombardment. Jupiter and Saturn changed their orbits. Resonances swept through populations of smaller bodies. Asteroids and comets were scattered inward. The terrestrial planets were bombarded. This gave Planet 5 serious competition. Why add an unseen fifth terrestrial planet if the known giant planets could destabilize the required material? Later work complicated the picture again. Evidence increasingly suggested that giant planet instability may have occurred much earlier than the classic late timing. Some models place it within the first tens or perhaps 100 million years of solar system history. If so, it cannot neatly explain a sudden bombardment beginning around 3.9 billion years ago. But if the bombardment itself was not sudden, that may no longer be a problem. Notice what keeps happening. Change the interpretation of the lunar rocks, and the required dynamical model changes. Change the timing of giant planet migration, and the interpretation of the rocks changes again. Discover an older lunar impact age, and another piece must move. Planet Futhiv is part of this larger process. It was never standing alone as the only possible explanation. It was one proposed mechanism in a changing reconstruction of an era for which our evidence is incomplete. Still, the basic image of the early inner solar system remains violent. Whatever exact curve we draw for the impact rate, large collisions were much more common than they are now. Consider how unusual a giant impact feels today. Human civilization has never witnessed an asteroid create a basin hundreds of kilometers across. Fortunately, the Chicxulub impact that occurred about 66 million years ago and contributed to the extinction of the non-avian dinosaurs produced a crater roughly 180 kilometers wide. It was an extraordinary event by modern standards. The early moon contains basins many times larger. Imbrium is over 1,000 kilometers across. Oriental is nearly 1,000. South Pole Aitken is vastly larger still. The impactors responsible were not everyday asteroids. They carried enough energy to reshape regional geology on a planetary scale. And during the basin-forming period, such collisions happened repeatedly. Not every year, not every century, probably not even every 100,000 years, but repeatedly enough that viewed across a few 100 million years, the terrestrial planets accumulated a remarkable amount of damage. This difference in timescale is worth keeping in mind. If you were somehow standing safely on the moon during the bombardment, you would not necessarily see another asteroid strike every time you looked up. Most days would contain no giant impact at all. Most years would not. Human civilizations could rise and fall between some basin-forming events. Geologists compress those intervals because the entire period is ancient. The word bombardment makes the process sound continuous. In reality, the impacts were individual catastrophes separated by long periods. Then another object arrived, a flash brighter than anything in the sky. Rock accelerated outward. The surface shook. Melt spread across the basin floor. Debris travelled hundreds or thousands of kilometres. Some lunar material escaped completely. Some of that material may eventually have reached Earth. The new crater then remained. Smaller impacts continued modifying it. Millions of years passed. Another enormous collision occurred elsewhere. Over time, the lunar highlands became saturated with craters. There is a point at which making a new crater destroys parts of older craters. The surface cannot record every impact independently forever. This phenomenon, known as crater saturation, makes the oldest bombardment even harder to reconstruct. Once a landscape becomes heavily cratered, additional collisions erase as well as create information. Counting craters no longer gives a simple, one-to-one measure of how many impacts occurred. The oldest pages of the lunar record have been repeatedly written over. This is one reason physical samples are so valuable. A rock can sometimes retain an isotopic age even when the original crater is difficult to identify, but samples introduce their own complications. A rock can be shocked more than once. It can contain fragments from different locations. Impact melt can mix material of different ages. Later heating can partially reset isotopic systems. The investigator has to determine which event the measured age actually represents. For Planet 5, all of this creates an uncomfortable but useful requirement. The hypothesis cannot simply point at a cratered moon and say, "That was me." The moon would be heavily cratered even without Planet 5. Planet formation already provides abundant early impactors. Giant planet dynamics can provide others. The asteroid belt has natural escape routes. Comets exist. The challenge is finding a distinct contribution that requires or strongly favours the missing planet. That is much harder. Perhaps Planet Favium could explain a delayed enhancement. Perhaps it could account for some late basins. Perhaps its disturbance of the inner asteroid belt would leave a recognisable signature in the surviving asteroid population. Or perhaps the same observations can be explained without it. For a hypothesis about a vanished planet to work, sooner or later the planet itself has to vanish. That sounds obvious until you try to make an object perhaps half the mass of Mars disappear without ruining everything around it. A planet is not a small piece of debris that can simply drift out of sight. Even a relatively modest rocky world contains an extraordinary amount of mass. If Planet 5 had half the mass of Mars, it would contain roughly 300 billion tons of material. You cannot tuck that behind an asteroid and hope nobody notices. Something physical had to happen to it. There are only a few basic options. It could collide with another planet. It could collide with the Sun. It could be thrown out of the solar system. It could, in principle, survive on some radically altered orbit. Although if a Mars-scale object were still travelling through the region between Mars and the asteroid belt today, we would know about it. Or perhaps Planet 5 never existed at all, which remains an option we must keep available throughout this story. The original simulations produced several of those outcomes, and the differences between them tell us why the Sun became such an important destination in the hypothesis. By the time Planet 5 was disturbing the asteroid belt, its orbit had already become highly eccentric. It was no longer travelling around the Sun in the relatively quiet, nearly circular path on which it began. Its closest distance to the Sun and its farthest distance from the Sun were becoming increasingly different. That brought it into contact with new regions of the solar system. Mars became reachable. The asteroid belt became reachable. Powerful resonances became reachable. And every time Planet 5 entered a new dynamical region, another set of gravitational interactions became available. The process did not need to happen in one dramatic encounter. A close passage by Mars could change the orbit. A resonance could gradually increase the eccentricity further. Another encounter could change the semi-major axis. Planet 5 might return to the same general region on its next revolution, but with a slightly different path. Eventually, one of those paths could become fatal. The most useful outcome for the original hypothesis was a collision with the Sun. That does not mean Planet 5 suddenly stopped orbiting and dropped straight downward. Objects orbiting the Sun possess sideways velocity. Earth is continuously falling toward the Sun under gravity, but it is also moving sideways quickly enough that it keeps missing. That is what an orbit is. To send a planet into the Sun, you usually need to remove enough of its angular momentum or alter its orbit so strongly that its perihelion, the closest point of its path, falls inside the Sun. Planet Phi could still spend most of its final orbit far away. Its path might stretch from the asteroid region down toward the central star. Each revolution would then carry it through a much greater range of distances and temperatures. At first, the perihelion might merely move inward toward the orbit of Mars. Later, it could pass inside Earth's orbital distance, then Venus, then Mercury. As the eccentricity continued increasing, the closest approach could shrink until the orbit physically intersected the Sun. There is no stable solid surface on the Sun for a planet to land on. The visible surface, called the photosphere, is hot plasma. A rocky world approaching it would experience an environment so extreme that words such as hot begin to lose some of their everyday usefulness. Solar radiation would intensify rapidly as the planet moved closer. Its surface would heat. Rock would melt. At sufficiently high temperatures, surface material would vaporize. Any atmosphere that had survived the previous billions of years would be exposed to intense radiation and solar interaction. The planet would also be moving extraordinarily quickly by the time it reached the inner solar system, because objects accelerate as they fall deeper into the Sun's gravitational field. Near the Sun, an object on an extremely elongated orbit can travel at several hundred kilometers per second. Planet 5 would not arrive as a recognizable little globe that gently disappears beneath a glowing surface. Its final approach would involve extreme heating, enormous velocity, and violent interaction with solar material. Exactly how much of the body would remain intact before direct impact would depend on its size, structure, trajectory, rotation, and how close it passed on previous orbits. The original Planet 5 calculations did not attempt to model those final geological details. For the dynamical problem, they were unnecessary. Once the planet's orbit intersected the Sun, Planet 5 had been removed as a separate member of the planetary system. Its atoms did not cease to exist. They became part of the Sun. That's worth emphasizing because saying that a planet fell into the Sun can make it sound as though the Sun swallowed it without noticing. The Sun would gain Planet V's mass, but even a Mars-sized world is tiny compared with the Sun. Mars has only about 3/10,000,000ths of the Sun's mass. A half-Mars Planet 5 would contribute roughly half of that again. For a star, this is not much. The Sun would not suddenly change colour, it would not become substantially brighter. Its gravitational control of the solar system would barely change. The planets would not notice a meaningful increase in the Sun's mass. From our perspective, 4 billion years later, there would be no obvious signs saying that an additional rocky planet had once joined the solar material. Stars are very good places to lose things. They are large, they are massive. They already contain almost everything in their planetary systems by mass. And unlike a collision with another planet, a collision with the Sun does not necessarily leave a surviving terrestrial world with an enormous new scar that we can examine today. That made the solar outcome attractive to Chambers and Lisauer. In their original set of 36 simulations, they tested Planet 5 at 3 different masses: 1/4 of Mars, 1/2 of Mars, and 1 Mars mass. The results were not all alike. For the smallest versions, those with 1/4 of Mars's mass, collision with the Sun was the most common result. 7 of the 12 simulations in that group ended with Planet Phi falling into the Sun. Most of the remaining runs ended with Planet 5 colliding with Mars. That second result was much less helpful. If Planet 5 survived for hundreds of millions of years and then hit Mars, the collision would be enormous. Even a 1/4 Mars mass body contains vastly more mass than the asteroid responsible for the extinction event at the end of the Cretaceous period on Earth. This would be a collision between planetary bodies. The energy could melt large regions. It could alter Mars's rotation. It could redistribute crust and mantle. It could add substantial material to the planet. Debris could be launched into orbit or completely away from Mars. The result would depend on speed and impact angle, but this would not be a small crater-producing event. It would be another giant impact. The authors therefore regarded late Planet 5 collisions with Mars as poor outcomes for their particular model. Their goal was to create a delayed bombardment while leaving the 4 known terrestrial planets broadly resembling their present forms. Having the missing planets solve one mystery by crashing into Mars and creating another was not particularly useful. Mars has certainly experienced enormous impacts during its history. 1 or more giant collisions have even been proposed to explain major features of the planet, including the striking difference between its northern and southern hemispheres. The relevant issue for Planet 5 is timing. A giant impact during the ordinary formation era is one thing. A large additional planet surviving for hundreds of millions of years, and then merging with Mars much later, would need to fit the geological and dynamical history of Mars as well. The original Planet 5 scenario was cleaner if the extra world disappeared into the Sun instead. The half-Mars versions produced a more mixed picture. 4 of the 12 fell into the Sun. 3 remained stable for the full 1 billion year duration of the simulation. Others ended in different unstable outcomes. This is a useful reminder that Planet V's disappearance was not automatic. Give the planet slightly different starting conditions and it might remain in the solar system far longer than required. If that had happened in reality, and the orbit remained somewhere beyond Mars, we would now have a 5th terrestrial planet. The fact that we do not means that any Planet 5 scenario must belong to the subset in which the object is eventually removed. The full Mars mass versions caused even more trouble. Only one of those 12 simulations ended with Planet 5 falling into the Sun. Most produced results that did not resemble the actual solar system. In some runs, Mars struck Earth. In others, Mercury fell into the Sun. The extraplanet was simply too effective at disturbing the terrestrial system. This helps explain why Planet V is usually imagined as smaller than Mars when the hypothesis is discussed. A missing planet does not merely need a plausible way to disappear. It needs to disappear while everybody we currently know survives. The larger a planet first becomes, the harder that requirement is to satisfy. There is another possible exit that sounds much cleaner. Why not simply eject Planet V from the solar system? Planetary ejection is real. We see the consequences of gravitational scattering in simulations of planetary systems, and astronomers have good reasons to believe that some planets can be expelled during periods of instability. A planet receiving the right sequence of gravitational encounters can gain enough energy that it is no longer gravitationally bound to its star. Its orbit changes from a closed ellipse into an open trajectory. It leaves. Eventually, the star becomes another distant point of light behind it. The planet then travels through interstellar space. Such objects are usually called rogue planets or free-floating planets, so perhaps Planet V is not destroyed at all. Perhaps it is still out there. It is a fun possibility. For this specific hypothesis, however, ejection is not the easiest outcome. Planet 5 begins deep inside the Sun's gravitational well. At around 1.8 or 1.9 astronomical units, it is much closer to the Sun than Jupiter. To eject it completely, something must give it enough orbital energy to escape the Sun. Mars can scatter Planet 5th, but Mars is small. Earth and Venus are more massive, but repeated encounters with them risk producing collisions or destroying the arrangement of the terrestrial planets. Jupiter is a much more effective planetary ejector, but Planet 5 would first need to reach an orbit that allowed encounters with Jupiter or undergo a suitable chain of interactions. Before that happens, there are many opportunities to hit the Sun or another inner planet. This is why small rocky bodies in the inner solar system often find the Sun an easier exit than interstellar space. Increasing eccentricity can reduce perihelion dramatically, without requiring enough energy to unbind the object completely. An orbit can become almost absurdly elongated, and still remain gravitationally attached to the Sun. Push the inner end of that ellipse far enough inward, and the Sun gets in the way. For the representative Planet 5 simulation, that is essentially what happened. The planet began around 1.9 astronomical units. It remained on non-crossing orbits with the known planets for several 100 million years. Around 400 million years into the calculation, its increasing eccentricity caused it to cross Mars and the inner asteroid belt. The disturbance of asteroids increased. Planet V's eccentricity and inclination then rose more rapidly. Eventually it entered the region associated with the NU6 secular resonance. By around 600 million years, its orbit carried it into the Sun. Notice the time scale. The planet could spend roughly 2/3 of its simulated life doing very little that looked catastrophic. Then about 200 million years could pass between the beginning of serious orbit crossing and its removal. Even the unstable stage was enormous by human standards. Planet 5 fell into the Sun compresses a complicated orbital history into 5 words. The actual process could involve millions upon millions of revolutions, perturbations, encounters, and gradual changes. The Sun was not waiting at the end like a drain pulling the planet inward. gravity does not work through that sort of friction in an ordinary planetary orbit. Planet 5 needed gravitational interactions that changed the shape and orientation of its trajectory. Once that trajectory became extreme enough, collision became possible. A third possibility is that Planet V struck Earth or Venus. Nothing in gravity fundamentally prevents this. Once an orbit becomes sufficiently eccentric to cross the terrestrial region, close encounters and collisions are available outcomes. A Planet 5 impact on Earth would be spectacular in the least useful sense of the word. Even a relatively small version of the planet would dwarf familiar asteroid impacts. The collision could melt large portions of Earth's surface, alter the mantle, affect rotation, and produce a huge debris disk depending on geometry. Earth had already experienced at least one event of roughly this general category earlier in its history, if the giant impact model for the Moon is correct. Adding another large collision hundreds of millions of years later would have to fit geological, isotopic, and lunar constraints. The original Planet 5 hypothesis did not rely on such an event. It needed Earth to collect smaller impactors, not the planet responsible for releasing them. Venus presents a slightly different problem because its ancient geological record is much harder to read. The present Venusian surface has been extensively modified, so a very old impact is more difficult to rule out from visible craters alone. Still, merging Planet 5 with Venus changes the mass and composition of Venus. A model would have to show that this final planet remained compatible with what we know today. Again, falling into the Sun avoids those complications. What about Mercury? A direct collision is dynamically possible in a sufficiently unstable inner system, although reaching Mercury from an initial orbit beyond Mars requires an extremely eccentric path. But Mercury itself proved fragile in some of the larger Planet 5 simulations. Rather than Planet 5 hitting Mercury, disturbances involving a Mars-mass extraplanet sometimes caused Mercury to fall into the Sun. That is a failure from the perspective of reconstructing our solar system. We still have Mercury. Any successful history must explain the missing object without accidentally deleting one that remains. There is also a more dramatic idea that often appears whenever a vanished planet is discussed. Perhaps Planet 5 exploded and became the asteroid belt. This is not what the Planet 5 hypothesis proposes. The asteroid belt existed as the population Planet 5 was supposed to disturb. It cannot simultaneously be the untouched reservoir waiting for Planet 5 and the debris created when Planet 5 was destroyed. More importantly, planets do not normally explode spontaneously. A rocky planet is held together strongly by its own gravity. Breaking one apart so thoroughly that the fragments permanently disperse requires an enormous input of energy. A giant collision could shatter and eject substantial material, but much of the debris can remain gravitationally bound and later reaccrete. The old idea that the asteroid belt represents a destroyed large planet has fallen out of favour for several reasons, including the belt's low total mass and its diverse composition. Asteroids are not simply pieces of one recently shattered Mars-sized world. Planet 5, if it existed, was a separate object moving among material that was already there. Could Planet 5 instead have been torn apart by the Sun before actually hitting it? Possibly, depending on how close its orbit brought it and how the body responded to tidal forces and heating. The side of a planet closer to the Sun feels a slightly stronger gravitational pull than the far side. Very close approaches can create large tidal stresses. For weak bodies such as some comets, solar encounters can produce dramatic fragmentation. A differentiated rocky planet is much more strongly bound than a fragile comet, so we should not casually imagine it breaking into convenient pieces as soon as it approached the Sun. Even if tidal or thermal disruption began before direct impact, however, the dynamical result would be similar for the hypothesis. The planet would cease to exist as an independent world, and much of its material could continue toward the Sun. There is one more possibility worth separating from the others. Could Planet 5 have been thrown outward, but remained bound to the Sun? Instead of being fully ejected, perhaps it acquired a distant eccentric orbit, and became a hidden planet somewhere beyond Neptune. Orbital scattering can move planets outward in principle, but there is no evidence connecting the proposed planet 5 with modern searches for a distant planet 9. They are different ideas addressing different problems. Planet 5 was proposed as a small terrestrial world formed between Mars and the asteroid belt. Planet 9, if it exists, is hypothesized from the orbital clustering of certain distant trans-Neptunian objects and would occupy an enormously more distant orbit. Turning one into the other would require a specific dynamical history that the standard Planet 5 model does not provide. It would also require Planet 5 to survive all the scattering needed to cross the giant planet region and emerge on a distant stable orbit. That is not impossible as a broad exercise in celestial mechanics. It is simply not evidence for the original hypothesis. There is no reason to combine two missing planets just because both are missing. Astronomy already has enough confusing names without arranging a reunion. If Planet 5 were instead completely ejected, identifying it today would be essentially hopeless. After roughly 4 billion years moving through the galaxy, a free-floating rocky planet could be an enormous distance from the Sun. It would receive almost no useful sunlight. Its surface would be extremely cold unless internal heat or some unusual atmosphere maintained warmer conditions. It would not carry a sign announcing its former address. Even if astronomers discovered a rogue planet with roughly the right mass, proving that it once orbited our Sun would be extraordinarily difficult. Its composition might resemble solar system material, but stars form from chemically related environments, and a small cold world offers few easy measurements. The Milky Way does not maintain a lost property office for planets. For the Planet 5 story, the Sun therefore remains the cleanest disappearance. Not because the simulations forced every possible extra planet into it. They did not. Not because planets naturally spiral into stars after enough time. Stable planets can orbit for billions of years without doing so. The solar collision works because the specific unstable pathways tested by Chambers and Lissauer could pump Planet Phi's eccentricity until its perihelion became extremely small. The planet then vanished from the terrestrial region without merging with one of the worlds we need to preserve. The Sun could absorb its modest mass without leaving an obvious planetary scar. The asteroid population Planet 5 had already disturbed could continue travelling inward after the planet itself was gone. For a while, the cause could disappear before all of its consequences had arrived. An asteroid scattered onto an Earth-crossing trajectory does not necessarily strike Earth immediately. It can survive through many orbits. The Moon can receive impacts after Planet 5 has already entered the Sun. Mars can continue encountering destabilized bodies. The population gradually declines as objects are removed. So there is no requirement for the final Planet 5 collision and the final bombardment crater to occur at the same moment. The dynamical system has memory in the form of altered orbits. That makes the disappearance unusually difficult to reconstruct billions of years later. If Planet 5 fell into the Sun, we cannot examine the planet. If its scattered asteroids later hit Earth, many of their craters are gone. If they hit the Moon, the craters remain but do not contain labels identifying who disturbed the impactors. If Planet 5 briefly altered the asteroid belt, billions of years of later collisions and resonances have modified that population further. Everything we might use as evidence is indirect. That is exactly where a hypothesis like this becomes scientifically vulnerable. Removing the planet is only half the job. A planet can disappear in a computer simulation very easily. What matters is whether the solar system left behind afterward looks like ours. Does Mars retain the right orbit? Does Earth? Does Mercury survive? Does the asteroid belt have a plausible structure? Do the timing and number of impacts agree with the lunar record? Can a reservoir large enough to produce the required bombardment exist without creating other contradictions? If Planet 5 really spent hundreds of millions of years beyond Mars and then died in the Sun, its body may be unavailable to us forever. But gravity is difficult to erase completely. A planet capable of moving asteroids, interacting with Mars, and altering the impact environment should have affected things that did survive. The search therefore has to move away from the missing planet itself. If Planet 5 fell into the Sun, there is no surviving world to inspect. If it was ejected from the solar system, finding it now would be extraordinarily unlikely. If it collided with another planet, the evidence would have to be extracted from geology that has been modified for roughly 4 billion years. So the investigation turns to everything that Planet Phi might have disturbed before it disappeared. The first place to look is the asteroid belt. That is appropriate because the belt was central to the original idea. Planet 5 was not proposed merely as an extra rocky world that happened to vanish. Its purpose in the model was to enter the inner asteroid belt, scatter objects onto unstable trajectories, and temporarily increase the number of impactors reaching Earth and the Moon. If that happened, the belt itself should have changed. Today, the main asteroid belt occupies the broad region between Mars and Jupiter, but its objects are not distributed evenly. There are gaps created by resonances. There are families produced by ancient collisions. There are groups with different inclinations and eccentricities. Some regions are densely populated compared with others. The inner edge is strongly shaped by gravitational effects involving the planets. Much of this structure can be explained without Planet 5. Jupiter alone has an enormous influence. Saturn contributes important secular resonances. Collisions continuously create fragments. Small thermal forces can gradually move asteroids into resonant locations. Planetary migration early in solar system history may have rearranged the belt substantially. This creates a problem for anyone trying to identify the work of a vanished fifth terrestrial planet. Planet Fayal would not be the only object capable of changing asteroid orbits. It would be one contributor in a system that has spent 4.5 billion years rearranging itself. A useful signature would therefore need to be distinctive. Suppose Planet 5 entered the inner belt and began scattering asteroids. Some objects would be removed completely. Some would move inward. Others would move outward. Eccentricities and inclinations could change. The population surviving after Planet 5 disappeared would not necessarily resemble the population that existed before it arrived. In principle, researchers could place a hypothetical asteroid belt into a computer simulation, add Planet 5, allow the system to evolve, and then compare the survivors with the real belt. If the final distribution looks wrong, that version of Planet Phi becomes less plausible. This is one of the strengths of celestial mechanics. A planet can vanish, but the orbits it disturbed do not instantly return to their previous values. Gravity does not include an undo button. Once an asteroid has been scattered, its new orbit becomes part of the later history of the solar system. Of course, 4 billion years of additional evolution can blur that record. Asteroids collide, families form, fragments migrate, resonances remove objects. The giant planets continue perturbing the belt. What survives today is a heavily processed population. Still, the broad structure places limits on what could have happened. You cannot place a giant planet in the middle of the asteroid belt for several 100 million years, allow it to clear almost everything, and then point to the present belt as though nothing unusual occurred. A successful Planet 5 must leave enough survivors. At the same time, the original hypothesis requires it to remove enough asteroids to matter. That is an uncomfortable balance. If Planet B barely disturbs the belt, it cannot generate much additional bombardment. If it disturbs the belt too strongly, the surviving asteroid population becomes difficult to reconcile with observations. Later researchers examined this problem quantitatively, and the results were not especially kind to the simplest version of the idea. In 2011, Rodney Brasser and Alessandro Morbidelli tested whether an unstable Planet 5 could actually release enough material from the asteroid belt to account for the scale of the late heavy bombardment as it was then understood. The question was straightforward. Chambers had already shown that an extraterrestrial planet could sometimes survive for hundreds of millions of years and later become unstable. But could that planet scatter enough asteroids toward the Moon? Those are separate questions. It is possible to create a beautifully unstable planet that produces a disappointingly small bombardment. Brasser and Morbidelli found that generating the required mass of lunar impactors from the main asteroid belt was extremely difficult. In one version, Planet 5 would need to be several lunar masses and cross essentially the entire asteroid belt, reaching as far as about 3.3 astronomical units, while remaining on a low-inclination belt-crossing orbit for more than 300 million years. Their simulations did not produce the required behaviour. Another possibility was to rely mainly on the inner belt. That created a different problem. To supply enough impactors, the inner region would have needed to contain several times more mass than the outer belt. That distribution was difficult to justify. This does not prove that an extra planet never existed. It weakens the claim that Planet 5, behaving as originally proposed, was responsible for the entire bombardment. The distinction is important. A hypothesis can lose its original job without the underlying object becoming physically impossible. Planet 5 may be dynamically possible while being unnecessary as the source of the lunar impact record. The Moon provides the second major place to search for consequences. If Planet 5 scattered a significant population of main belt asteroids into the inner solar system, some fraction should have struck the Moon. Those impacts would produce craters. The sizes of those craters contain information about the sizes of the impactors. This gives researchers something surprisingly useful. You cannot identify the asteroid that made most ancient lunar craters because the projectile was destroyed during impact. You can, however, study the overall crater population. Imagine measuring thousands of craters across an old lunar surface. Count how many are 10 kilometers wide, then 20, then 50, then 100. The resulting size-frequency distribution can be compared with the size distribution of possible source populations. If the ancient lunar impactors were random samples taken from the main asteroid belt, the pattern of crater sizes should reflect that source, after accounting for the physics that turns an impactor of one size into a crater of another size. Some studies have found similarities between the ancient crater population and the main asteroid belt. That initially seemed helpful for models in which a dynamical event suddenly removed asteroids from the belt. Planet faces could potentially provide such an event, but the match is not simple. Later modelling showed that using the modern main belt size distribution to produce the observed lunar highland craters can create too many extremely large basins. A population containing enough medium-sized impactors to reproduce the smaller ancient craters may also contain enough large objects that the Moon should have acquired several basins larger than anything actually observed. The Moon, inconveniently, appears to have avoided some of those expected enormous impacts. That means the ancient impactor population may have differed from the present asteroid belt. Perhaps the belt itself had a different size distribution. Perhaps the impactors came from more than one source. Perhaps leftover planetesimals dominated the earliest period while asteroids became more important later. Any of those possibilities makes it harder to use lunar craters as a clear fingerprint of Planet 5. There is another problem. Planet 5 was supposed to produce a delayed disturbance, so the ages of the resulting craters matter just as much as their sizes. If the planet became unstable about 600 or 700 million years after solar system formation, we should expect an enhancement in impactors around that general time. The old late heavy bombardment interpretation seemed to provide exactly such a feature near 3.9 billion years ago. Our picture of lunar bombardment has since become less certain. Older basin-forming impacts are now recognised. The idea of one narrow cataclysm has been questioned. A long declining bombardment may explain part of the record. Several source populations may overlap. That makes it difficult to point to one cluster of lunar scars and say that Planet 5 produced them. The craters are certainly real. Their exact source is the difficult part. Mars offers another possible record. A planet V moving between roughly 1.8 and 2 astronomical units would have lived immediately beyond Mars. Once its orbit became eccentric, Mars would be the first major planet directly exposed to close encounters. That means Mars could carry two kinds of evidence. The first is impact damage from asteroids scattered inward. The second is orbital or geological evidence from encounters with Planet 5 itself. The Martian surface certainly preserves ancient bombardment. Its southern highlands are covered with old craters. Large basins such as Hellas, and Argyre record enormous early collisions. The challenge is the same one we encountered on the Moon. Those scars do not identify the mechanism that supplied the impactors. Mars was being bombarded before Planet 5 would have become unstable. Leftover planetesimals, asteroids and other populations were already present. A crater is evidence of an impact. It is not automatically evidence of Planet 5. A direct collision would be much more distinctive. If Planet Phi struck Mars hundreds of millions of years after the initial formation period, the event could dramatically alter the planet. Some Planet Phi simulations did produce exactly that outcome. From the point of view of the hypothesis, those runs are usually treated as failures rather than evidence. A late collision involving a large fraction of Mars's own mass would have consequences that need to be compatible with the real Mars. Its mantle, crust, rotation, satellites, and large-scale geology would all become relevant. Mars does possess one feature so large that giant impacts are frequently discussed as an explanation: the hemispheric dichotomy. The northern lowlands sit several kilometres lower than much of the southern highlands. One class of models proposes that an enormous impact early in Martian history helped create this difference. It is tempting to connect that directly to Planet 5. We should not. There is no established evidence identifying Planet 5 as the impactor responsible for the Martian dichotomy. The timing, impact geometry, mass of the projectile and competing formation models make that connection speculative. A large ancient scar is not automatically the grave of whichever hypothetical planet happens to be available. Mercury gives us another heavily cratered surface, but the same caution applies. If Planet 5 scattered asteroids inward, Mercury would have received some of them. Mercury's oldest terrain certainly experienced intense bombardment. The Caloris Basin demonstrates that enormous objects reach the planet, yet there is no known Mercurian crater whose properties require a Planet 5 source. The asteroid that made Caloris does not come with an orbital history preserved in the rock. Scientists can estimate the impactor's size and velocity range. They cannot reconstruct a 4 billion-year-old gravitational encounter with a vanished planet from the basin alone. Earth is even less cooperative. If Planet 5 caused a major increase in inner solar system impacts, Earth should have received more impacts than the Moon because Earth is larger and has stronger gravitational focusing. Most evidence is gone. The crust from Earth's first several hundred million years has been heavily reworked. Plate tectonics recycles material, weather destroys craters, oceans hide them, sedimentary processes bury them, volcanism covers them. A large impact can leave geochemical signals, but identifying a specific dynamical source billions of years later is extraordinarily difficult. There is no known layer in Earth's oldest rocks that can be confidently labelled as debris delivered, because Planet has crossed the asteroid belt. Meteorites might seem more promising. If Planet V was a differentiated rocky world, perhaps fragments of it survived. We already possess meteorites from Mars. Some meteorites came from the Moon. Many others can be connected to asteroid parent bodies. Fragments of the asteroid Vesta have been identified through matching mineralogy and spectral observations. Could one of the unclassified meteorite groups come from Planet Fifth? It is possible in the broadest sense that material from a destroyed planetary embryo could survive as meteorites. The early solar system contained many differentiated bodies. Some no longer exist as intact objects. Meteorites preserve fragments of that history. The problem is identification. There is currently no meteorite group accepted as material from Planet 5. To establish such an origin, scientists would need distinctive chemical and isotopic evidence showing that the meteorites came from a separate differentiated parent body, followed by a plausible mechanism for getting fragments from that world onto trajectories that survived until much later. Even then, proving that the parent body was specifically the planet Viv Chambers and Lissauer would be difficult. A meteorite from a destroyed planetary embryo is not automatically a meteorite from planet V. There were many embryos during terrestrial planet formation. Naming the parent requires more than demonstrating that it once had enough heat to separate into a core and mantle. The Sun, despite being Planet V's most convenient final destination, is probably the least useful place to search for a recognizable scar. Suppose half a Mars mass entered the Sun. That sounds like an extraordinary amount of rock. Compared with the Sun, it is tiny. The material would mix into a star containing hundreds of thousands of Earth masses. Planet V's addition would not produce a recognizable mark on the photosphere lasting 4 billion years. The Sun's outer layers circulate. Elements are transported. The star evolves. Even if the infalling planet temporarily produced an energetic disturbance, that event happened before complex life existed on Earth and left no photograph for us to inspect. In principle, astronomers study stellar composition to learn whether stars have consumed planetary material. Certain chemical abundance patterns can sometimes suggest that a star accreted rocky bodies. Doing this for our own Sun and identifying one particular hypothetical planet swallowed billions of years ago is another matter. The solar system began with uncertainties in its initial chemical distribution. The Sun has consumed other small bodies. Material continued falling inward during formation. Separating one Planet 5 from all of that would be extremely difficult. The strongest scars may therefore be dynamical rather than geological. Look at the surviving planetary orbits. Earth is still here. Mars is still here. Venus and Mercury survive. The Moon remains gravitationally bound to Earth on an orbit that has evolved through tidal interactions for billions of years. Any Planet V's history must leave these bodies in acceptable final states. That means the lack of obvious disruption becomes a constraint. This is a slightly unusual kind of evidence. We are searching for what did not happen. Planet 5 did not eject Earth. It did not merge Earth and Venus. It did not remove Mars. It did not send Mercury permanently out of the solar system. At least, not in the history that produced the system we see. Chambers revisited the stability problem in 2007 with 96 numerical integrations containing an additional body between Mars and the asteroid belt. The results showed that long-delayed instability was not an impossible trick found in one fortunate simulation. More than a quarter of the extra planets survived for the full 1 billion year integration. In many other runs, the fifth planet lasted hundreds of millions of years and then collided with the Sun or another planet. 24 of the 96 simulations managed to remove Planet 5 by ejection or collision with the Sun while preserving the other 4 terrestrial planets without a collision. That is a significant result. It means there are plausible gravitational histories in which an extra world disappears and the familiar terrestrial planets remain. But it also tells us something awkward. Many different histories are possible. The current orbits do not uniquely point backward to one Planet 5. A 4-planet solar system can result from many initial configurations. The fact that a fifth body can be removed does not prove that one was. There may also be clues in a population of small asteroids occupying the region just beyond Mars. The Hungaria asteroids orbit mainly around 1.8 to 2 astronomical units and tend to have relatively high inclinations. That location is interesting because it overlaps the broad neighbourhood in which hypothetical long-lived bodies and ancient Mars-crossing populations have been studied. Researchers have proposed that the Hungarias may be remnants of a much larger primordial population of Mars crossers. Such a population could have supplied impactors to the terrestrial planets for hundreds of millions of years. This provides another route to ancient bombardment that does not require Planet 5 to release the material. The small survivors themselves may represent the long tail of a population gradually leaking away. Again, something that initially looks like evidence for Planet 5 can become competition for Planet 5. If the region beyond Mars naturally stored impactors for hundreds of millions of years, then perhaps no fifth planet was needed to create a delayed supply. This is one of the recurring themes in reconstructing the early solar system. A proposed clue rarely belongs to one explanation alone. The Moon is cratered because objects hit it. That is certain. The asteroid belt is depleted and dynamically structured. That is certain. Mars has enormous ancient impact basins. That is certain. Populations of small bodies can survive in niches for very long periods. That is certain. The uncertain part is connecting those facts into one specific history. Planet 5 offers one connection. Other models offer others. Consider what a genuine smoking gun would look like. Imagine that scientists discovered a family of meteorites with unique isotopic composition, showing they came from a differentiated planet formed specifically around 1.9 astronomical units. Suppose their ages indicated catastrophic surface disruption at exactly the time Planet 5 became unstable. Then imagine orbital models showing that no known asteroid parent body could deliver those fragments, but a fifth terrestrial planet could. That would be interesting. We do not have such evidence. Or suppose the asteroid belt contained a sharp dynamical feature that could only be produced by a half-Mars mass planet crossing a particular region for 100 million years. That would also be powerful. No uniquely planet V-shaped feature has been identified. Perhaps lunar craters could provide the signature. If they showed a sudden bombardment at exactly the predicted time, with impactor sizes and compositions matching the exact part of the belt Planet 5 would disturb, and competing mechanisms could not reproduce the pattern, the case would strengthen substantially. The real lunar record is not that clean. This does not mean Planet 5 leaves no testable consequences. Quite the opposite. It means there are many tests, and the hypothesis must survive all of them together. The extraplanet must remain stable for the correct amount of time. It must become unstable without destroying the terrestrial planets. It must cross enough of the asteroid population to release impactors. It must release enough mass. The size distribution of those impactors must be reasonable. The asteroid belt left behind must resemble the belt we observe. The lunar impact chronology must fit. Mars and Mercury must remain compatible with their known histories. Planet 5 itself must then be removed. Each requirement narrows the range of successful scenarios. This is why the scars left by a vanished planet are not likely to be one enormous crater with an obvious explanation. They would be a combination of orbital distributions, impact statistics, surviving populations, missing populations, geological ages, and probabilities. No single clue is enough. Researchers have to make all of them agree within one gravitational history. That is also why Planet 5 became a particularly suitable problem for numerical modelling. You cannot rebuild the early solar system experimentally at full scale. There is no spare sun available for testing. We cannot place another Mars beyond the real Mars, leave it there for 600 million years, and see what happens. The equations of gravity provide another option. Construct the solar system mathematically, add the missing world, give it a mass, choose its starting orbit, add thousands of asteroids, run the clock forward, then change one number and do it again. One planet Phi falls into the Sun, another hits Mars, another survives, another enters the asteroid belt but releases too few objects. One version destabilizes the terrestrial planets, a different version leaves them almost untouched. After enough experiments, patterns begin to emerge. The question stops being simply whether a vanished planet sounds possible. It becomes a measurable question about how often the required sequence of events actually occurs, what traces that sequence leaves behind, and whether those traces resemble the solar system that survived. The closest thing planetary scientists have to watching the crime happen is to rebuild it inside a computer and run the solar system again. Obviously, this is not quite the same as creating another real solar system. There is no miniature sun glowing inside the computer. Mars is not reduced to the size of a pea and placed beside a very nervous group of asteroids. Instead, researchers describe each important body using numbers: mass, position, velocity, orbital eccentricity, inclination, the orientation of the orbit. Then they tell the computer how gravity works and allow those numbers to evolve. The basic physics is familiar. Every massive object attracts every other massive object. The strength of that attraction depends on the masses involved and the distance between them. Newton worked out the essential mathematics centuries ago. The difficult part is not knowing the gravitational law. The difficult part is applying it millions upon millions of times to several moving bodies whose positions are continuously changing. If you only have the Sun and one planet, the problem is relatively neat. Add Earth, Mars, Venus, Jupiter, Saturn, and an extra hypothetical planet, and every object is now responding to several gravitational influences at once. Add thousands of asteroids, and the bookkeeping becomes much less pleasant. Fortunately, computers are remarkably tolerant of unpleasant bookkeeping. A numerical integration breaks the history into small steps. The computer calculates the gravitational forces, it updates the positions and velocities, then it moves forward another step, and another, and another. Millions of simulated years can be built from an enormous sequence of these calculations. Choosing the size of those steps matters. Make them too large and the simulation can miss important details, especially during close encounters. Make them extremely small and the calculation becomes painfully slow. Planetary scientists therefore use numerical methods designed specifically for long-term gravitational systems. One common family is known as symplectic integrators. These are particularly useful for orbital dynamics because they do a good job of preserving important properties of a gravitational system over very long integrations. They are not magically exact. No numerical simulation is, but they are designed to prevent small computational errors from accumulating in ways that would make a planet slowly gain energy simply because the computer has been rounding numbers for several 100 million simulated years. That would be an embarrassing way to discover a new planet. Chambers used this general approach to investigate Planet 5. The question was not initially, can we make one simulation in which an extra planet falls into the Sun? That would be relatively easy. Give a planet an obviously unstable orbit and it can disappear very quickly. The interesting question was much more specific. Can the known solar system contain an additional terrestrial planet beyond Mars, keep it for several 100 million years, and then remove it while Mercury, Venus, Earth and Mars survive? That is harder. The starting conditions have to be believable. The delay has to be long enough. The disappearance has to happen. And the remaining planets have to look reasonably similar to the ones we observe. In the 2007 study, Chambers performed 96 long-term numerical integrations containing the major planets and one extra body between Mars and the asteroid belt. The simulations explored different masses and orbital configurations for Planet 5. Some results were uneventful. The fifth planet simply survived. After 1 billion simulated years, it was still orbiting. From the point of view of a stable 5-planet system, that is perfectly respectable. From the point of view of explaining why Planet 5 is missing today, it is a failure. Other runs ended much sooner. The extra planet hit another planet. Sometimes the terrestrial system became excessively disturbed. Again, those outcomes are dynamically possible. They simply do not resemble the history that produced our present solar system. Then there were the useful cases. Planet 5 survived for hundreds of millions of years. Its orbit gradually became unstable. It was eventually ejected or collided with the Sun, and the 4 familiar terrestrial planets remained without suffering a collision. 24 of the 96 integrations produced that broad type of result. That is not proof that Planet 5 existed. It is something more modest. It shows that the disappearance scenario is not dynamically absurd. Gravity can do it. A 5th terrestrial planet does not automatically destroy the solar system. Under some starting conditions, it can remain for a long time and then be removed. That result is exactly why computer experiments are valuable. Without them, we might look at the empty region beyond Mars and casually say that another planet could never have survived there. Or we might make the opposite mistake and assume that if it formed there, it should still be there. Numerical integrations allow those statements to be tested. They show that the real answer can lie in between. Some orbits are short-lived, some survive much longer, some last longer than the timescale required by the Planet 4 hypothesis. The outcome depends sensitively on the initial conditions. That sensitivity creates another problem. If you can produce many different solar systems by adjusting a few starting values, how do you know which one resembles the real past? You do not simply choose your favourite, you compare the outcomes with evidence. Earth's final orbit matters. Mars's eccentricity matters. The asteroid belt matters. The timing of impacts matters. The amount of surviving material matters. The simulation has to earn its way into the historical explanation. This is where researchers often run many versions of the same basic experiment. Change planet V's mass. Run again. Move its starting orbit slightly inward. Run again. Increase the inclination. Run again. Change the orbital phase. Run again. One extra planet may hit Mars after 40 million years. The next survives 600 million. Another falls into the Sun after 200 million. One destabilizes Mercury. Another barely affects anything. This may look like the computer cannot make up its mind. The computer is doing exactly what it should. Chaotic systems can amplify small differences. The solar system is deterministic in the sense that gravity follows physical laws, but long-term orbital evolution can still be chaotic. That word does not mean random in the everyday sense. It means that tiny differences in the starting state can eventually produce large differences in the outcome. Imagine two planet Vs beginning on almost identical orbits. At first, their paths are nearly indistinguishable. After 1 million years, the difference is still small. Eventually, one passes Mars slightly closer than the other. That close approach changes its velocity. The next encounter now happens at a different angle. The paths separate more. Hundreds of millions of years later, one planet 5 may be inside the Sun while the other continues orbiting peacefully. The difference began with something that once looked insignificant. This is why researchers care about probabilities and populations of simulations rather than one beautifully dramatic run. A successful simulation tells you something can happen. A large ensemble begins telling you how readily it happens under the tested assumptions. Planet 5 passed the first test. It could disappear late. The next test was much less comfortable. Could it actually produce the bombardment it had been invented to explain? This required adding small bodies. Instead of following only the planets, researchers had to populate possible asteroid reservoirs and watch what happened when Planet 5 became unstable. The asteroids could often be treated as test particles. They feel the gravity of the planets. They do not significantly affect the planets themselves. That saves a considerable amount of computation. An asteroid's gravitational pull on Jupiter is technically real. Jupiter is simply unlikely to lose sleep over it. Brasser and Morbidelli later performed a much more detailed examination of this part of the Planet 5 scenario. Their simulations included the Sun, Venus, Earth, Mars, Planet 5, Jupiter, and Saturn. They used a numerical integrator capable of following close planetary encounters. They also tested small body populations in the main asteroid belt and hypothetical reservoirs between the terrestrial planets. This time, the question was not merely whether the extra planet disappeared correctly. They wanted to count the material it could release. That is where an appealing story runs into arithmetic. To reproduce the traditional estimate for the late heavy bombardment, enough mass has to reach the Moon. The Moon only intercepts a tiny fraction of objects scattered into the inner solar system. Most asteroids never hit it. Some strike Earth, some reach Venus, some hit Mars, some fall into the Sun, some are ejected from useful impact trajectories. Many simply miss everything for a very long time. So if the lunar surface requires a certain amount of impactor mass, the original reservoir has to contain considerably more. Planet 5 therefore needed to scatter a very large population. Brasser and Morbidelli tested Planet 5 masses ranging from roughly 1 lunar mass to 10 lunar masses in parts of their experiment. They also explored different starting orbits. They ran hundreds of simulations of the planetary system and additional integrations containing small bodies. A computer cluster handled calculations that would be rather inconvenient to complete with pencil and paper. Some individual runs took months of real computing time. That is another useful detail about these reconstructions. When we casually say, scientists simulated 500 million years, the computer did not simply press fast forward. It calculated vast numbers of gravitational interactions. Long integrations involving close encounters and many particles can be computationally expensive even when the equations themselves are well understood. The results created trouble for Planet Viv. If the main asteroid belt was supposed to supply enough material for the traditional bombardment, the extra planet needed to disturb a large portion of it. The researchers found that a planet foe of at least several lunar masses would have to cross essentially the entire asteroid belt, reaching outward to around 3.3 astronomical units, and remain on a low inclination belt crossing orbit for more than 300 million years. That is a very demanding requirement. The planet cannot merely clip the inner edge of the belt for a few million years. It has to spend a long time travelling through a broad range of asteroid territory without disappearing too soon. In more than 100 relevant simulations, Brasser and Morbidelli did not see the required behaviour. That is bad news if Planet V's main job is to generate the whole late heavy bombardment from the asteroid belt. Another approach was to concentrate much more material in the inner asteroid belt. Then Planet V would not need to cross so far outward. But the numbers again became uncomfortable. The inner belt would need to contain roughly 4 to 13 times more mass than the outer portion in the scenarios they examined. There was no strong independent reason to expect such an extreme distribution. You can always make a model work by adding enough unseen material in exactly the right place. The scientific question is whether that added material is plausible for reasons other than saving the model. Researchers also considered hypothetical belts of small objects between Venus and Earth and between Earth and Mars. Long-lived niches can exist in some parts of those regions. If large populations once survived there, Planet V's instability might release additional impactors. Again, however, the distribution had to satisfy particular requirements. One reservoir needed to contain substantial material, while another had to be nearly empty. The scenario could be arranged, but it was becoming increasingly specialized. This illustrates something important about computer modeling. A simulation is not a machine that transforms an interesting idea into truth. It is often much better at finding the idea's problems. That is one of its most useful functions. You propose Planet 5. The computer says a fifth world can sometimes survive for hundreds of millions of years. Excellent. You ask whether it can vanish while Earth and Mars remain. Sometimes yes. Excellent again. You ask whether it scatters asteroids. Yes. Very encouraging. Then you ask whether it scatters enough asteroids, for long enough, from the correct places, while preserving the right belt afterward. The computer becomes less enthusiastic. Science advances through this narrowing process. A hypothesis begins broad. Tests remove possibilities. Sometimes the original idea survives with modifications. Sometimes one piece survives while the larger explanation is abandoned. Sometimes a completely different model explains the evidence with fewer special conditions. Planet 5 increasingly found itself in the second category. Its long-delayed dynamical instability remained interesting. Its ability to explain the entire traditional late-heavy bombardment became much harder to defend. There is another issue computers cannot solve by themselves. A numerical model only answers the problem you give it. If your starting picture of lunar bombardment is wrong, a perfect simulation of that picture may still produce the wrong history. Suppose you require a sudden spike in impacts at 3.9 billion years, because that is what the lunar samples appear to show. You then search for a mechanism capable of producing the spike. Planet Farth might be one candidate. Giant planet migration might be another. A disrupted asteroid might be another. But if later evidence shows that the lunar bombardment was spread across a much longer interval, the original target changes. Now, the best model may be one that produces a prolonged decline with several overlapping sources rather than one enormous delayed pulse. This has become increasingly relevant. Our understanding of ancient lunar impacts has continued changing as new samples, improved dating methods, meteorites, and remote observations become available. The largest visible basin on the Moon, South Pole Aitken, may date to roughly 4.33 billion years ago, according to recent work using a lunar meteorite linked compositionally to the basin region. If that interpretation is correct, a giant basin-forming event happened around 120 million years before the main cluster of later lunar basins. That weakens the simplest picture in which the Moon enjoyed a long, quiet interval, and then suddenly entered one narrow period of catastrophic bombardment around 3.9 billion years ago. The evidence increasingly encourages a more complicated history. And complicated histories are perfectly acceptable. Nature is under no obligation to choose the easiest graph for us to draw. Modern models often consider several impactor populations. Leftover planetesimals from terrestrial planet formation can provide an early declining flux. Asteroids destabilized by changes in planetary architecture can contribute later. Comets and other outer solar system populations may add another component. Different mechanisms can overlap. The impact record we see may be the sum of several processes rather than the signature of one trigger. For Planet 5, that changes the question yet again. Instead of asking, can a fifth planet explain every late lunar basin? We can ask, could an extraterrestrial planet have existed and contributed to the evolving impact environment? The second question is much easier to answer positively. The simulations show that such a body can exist under some conditions. It can become unstable, it can scatter small bodies, it can disappear. Nothing about that violates celestial mechanics. But once the requirement becomes merely possible rather than necessary, the evidential standard changes. There are countless things the early solar system could have done. We want to know what it actually did. Computer simulations help by constructing possible histories and eliminating many of them. They cannot retrieve the past with perfect uniqueness. There is no save file from 4.2 billion years ago. The system we observe today is the end product. Many different starting arrangements can sometimes converge on similar final ones. That is why researchers combine simulations with geology, geochemistry, crater statistics, meteorites, isotopic ages, and observations of other planetary systems. Each source of evidence removes more possibilities. Planet 5 has survived an interesting subset of those tests. A fifth terrestrial body beyond Mars is dynamically conceivable. Long-delayed removal is dynamically conceivable. A solar collision is conceivable. Asteroid scattering is inevitable once such a body begins crossing the belt. What has not emerged is a unique requirement for the planet. The simulations do not return a message saying, "Solar system reconstruction complete. Missing object identified." Instead, they give probabilities, ranges, failed runs, successful runs, conditions that are easy to produce, conditions that require very specific arrangements. And those results leave us with the uncomfortable question that has been waiting behind the entire story. We have shown how Planet 5 could be born. We have shown how it could remain hidden in plain sight beyond Mars for hundreds of millions of years. We have shown how its orbit could become unstable. We have watched it enter the asteroid belt. We have followed the asteroids scattered toward the inner planets. We have found ways for the planet itself to disappear. We have even rebuilt the sequence inside computers and demonstrated that gravity permits much of it. But possibility is not evidence of existence. So after all the simulations are finished running, the harder task is to close the computer, look at the actual solar system, and ask. That is the harder question. Did Planet Phi ever really exist? At the moment, the scientifically responsible answer is that we do not know, and there is no direct evidence proving that it did. That may feel slightly unsatisfying after spending so much time following a planet, from birth to destruction. We have given it an orbit. We have watched Mars perturb it. We have sent it through the asteroid belt. We have scattered impactors. We have allowed resonances to stretch its path toward the sun. After all that, it would be convenient to finish by saying that scientists have now confirmed the missing world, and everyone may update their solar system posters accordingly. They have not. Planet 5 remains hypothetical. It is a proposed additional terrestrial planet whose existence was explored because it offered an interesting possible explanation for the early bombardment of the inner solar system. The distinction between possible and demonstrated is the most important thing to keep in mind. There are good reasons to believe that the early solar system contained more planetary embryos than the planets we see today. That is not controversial. Terrestrial planet formation requires many large bodies to collide, merge, and scatter. Theia, the hypothetical impactor involved in the Moon's formation, is one famous example of a major body that no longer exists independently. Meteorites also show that differentiated parent bodies formed and were later disrupted. Numerical models regularly produce planetary embryos that disappear during the formation period. So the general statement that the solar system once contained lost worlds is almost certainly true. The specific statement that one particular sub-Mars-sized planet survived beyond Mars for roughly 500 million years and then triggered a late bombardment is much more demanding. That is Planet 5, and evidence for that exact history is weak. The original motivation came from a problem that itself has changed. When Planet 5 was introduced, the late heavy bombardment was widely discussed as a relatively sudden spike in lunar impacts around 3.9 billion years ago. If the Moon had experienced a long period of declining impacts followed by an abrupt renewed bombardment, something had to destabilize a fresh population of projectiles. A delayed planetary instability was one clever way to do it. Planet 5 could remain quiet. Then it could become unstable. Then it could scatter asteroids. Then it could disappear. The timing gave the hypothesis its purpose, but lunar science did not stop in 2002. Apollo samples were reanalyzed. Lunar meteorites provided material from regions not visited by Apollo astronauts. Crater chronology improved. Remote sensing mapped the Moon in greater detail. New sample return missions began adding information from previously unsampled locations. The simple cataclysm picture became increasingly difficult to treat as settled. NASA's current discussion of the late heavy bombardment describes the subject as controversial. The impact history may have been gradual. It may have contained several episodes. There may not have been a narrow spike at all. The Apollo samples cover only a limited portion of the lunar surface, and material from enormous impacts such as Imbrium can be distributed over large areas. Several rocks recording similar ages may therefore represent fewer independent impacts than once assumed. Meanwhile, evidence for older basin-forming events keeps appearing. A recently proposed age for the South Pole Aitken Basin places that enormous collision at around 4.33 billion years ago. That is significantly earlier than the classic 3.9 billion year cataclysm. If the Moon was already forming giant basins that early, then the bombardment cannot be described simply as a quiet period followed by one sudden late storm. That does not mean nothing unusual happened near 3.9 billion years ago. Imbrium and other major events certainly occurred around that broad era. The question is whether they represented a special spike requiring a specific trigger. If there was no sharp spike, Planet 5 loses much of the job for which it was invented. A hypothesis can survive the disappearance of its original motivation, but it needs another reason to remain attractive. Perhaps an extraplanet beyond Mars helps explain some other feature. Perhaps it contributes to the unusual small mass of Mars. Perhaps it affects asteroid populations in a useful way. Perhaps meteorites eventually reveal material from an appropriate parent body. Those possibilities can be explored. At present, none provides a widely accepted detection of Planet 5. There is also competition from more comprehensive models of solar system evolution. The giant planets almost certainly played a major role in rearranging small body populations. Jupiter and Saturn strongly control the asteroid belt's resonant structure. Uranus and Neptune influence the outer disk. Models involving migration and instability of the giant planets can send asteroids and icy bodies toward the terrestrial region. The timing and exact architecture of that instability remain active research questions, but the mechanism uses planets that we know exist. That gives it an immediate advantage. When two models explain the same observation, scientists generally prefer not to add an invisible planet unless the extra object solves something the known planets cannot. This is not a rigid rule that hypothetical objects are forbidden. Neptune was hypothetical before it was observed. Exoplanets are routinely inferred from indirect effects before anyone can image them. Dark matter is inferred because multiple lines of evidence indicate additional gravitating mass. The key is necessity. If observations repeatedly demand an unseen object, the lack of a direct photograph is not a fatal problem. Planet 5 has not reached that position. No unexplained gravitational effect in the current solar system requires a missing planet once to have orbited at 1.9 astronomical units. No asteroid family has been uniquely traced to a Planet 5 encounter. No lunar basin has been identified as a definite consequence of its instability. No Martian scar requires that particular impactor. No meteorite has been confidently labelled a surviving fragment of Planet 5. The hypothesis is therefore judged mainly by whether its proposed history provides a useful explanation for known features. That explanation became less compelling when quantitative simulations tested the amount of material it could deliver. This was one of the most damaging results. It is easy to say that Planet Vera enters the belt and scatters asteroids. Of course it would. A planetary embryo moving through an asteroid population will perturb objects. The difficult question is whether the numbers are sufficient. Brasser and Morbidelli found that producing the traditionally estimated lunar bombardment from the main belt required demanding conditions. The several lunar mass Planet 5 would need to cross a large portion of the belt for hundreds of millions of years on an appropriate orbit. Their simulations did not naturally produce that behaviour. Concentrating the necessary material in the inner belt required an unusually massive inner population. Other hypothetical reservoirs could help only under specialised assumptions. This weakens Planet 5 as the main engine of the late heavy bombardment. Notice that the result does not say Planet 5 cannot exist. It says something more precise. The proposed object has difficulty performing the particular task assigned to it. That is an important scientific distinction. Imagine discovering that a suspect in a mystery really could have been in the city on the correct day. That establishes opportunity. Then you discover the suspect could not physically have carried the object involved in the crime. Opportunity remains. The case does not. Planet 5 has plenty of dynamical opportunity. Its responsibility for the bombardment is much harder to establish. The current solar system also fails to provide a clear dynamical fingerprint of its former presence. Chambers showed that an extraterrestrial planet can sometimes be removed while the surviving planets remain. That is useful for showing plausibility. It is less useful for proving history precisely because the survivors can look reasonably normal afterward. If Planet Phi always left Mars with an eccentricity twice the observed value, we could reject it easily. If it always created a distinctive gap in the asteroid belt, we could search for that gap. If its removal inevitably tilted Earth's orbit by a measurable amount, the present Earth could provide a test. Instead, some successful simulations remove the extra world without leaving an obvious unique signature. The better Planet 5 becomes at disappearing cleanly, the harder it becomes to prove that it was ever there. This is not unusual in ancient planetary science. Many early objects leave ambiguous evidence because subsequent evolution erases or mixes their effects. Consider Theia. We do not have a planet labelled Theia orbiting nearby. The case for a giant moon-forming impact comes from the Earth-Moon system itself, angular momentum, geochemistry, isotopic measurements, lunar formation models, and numerical impact simulations. Even there, major details remain debated. What was Theia's mass? Where did it form? How energetic was the collision? How much material in the moon came from Earth versus the impactor? Scientists can argue over those questions because a giant impact origin solves several features of the Earth-Moon system at once. Planet Phi does not have an equivalent collection of independent clues pointing toward it. That could change. Future lunar samples are particularly valuable. The Moon remains our best archive of early inner solar system impacts. Samples from precisely chosen basins could provide absolute ages for events that are currently ordered mainly through crater relationships. If South Pole Aitken, Nectaris, Serenitatis, Imbrium, Orientale and other large basins can be dated more reliably, scientists can reconstruct the bombardment curve with much greater confidence. A clear chronology would immediately improve test of dynamical models. Suppose future samples show that basin formation truly was concentrated in a narrow interval after a long quiet period. Then delayed instability models regain importance. Planet Phi might deserve another look, although it would still face the mass delivery problem. Suppose instead that the basins formed gradually from more than 4.3 billion years ago through roughly 3.8 billion years ago. Then a single late trigger becomes less necessary. A declining population of leftover planetesimals combined with later asteroid delivery might fit better. Either result tells us something important. Mars can contribute as well. Future sample return missions from carefully selected ancient Martian terrains could improve absolute crater chronology for another terrestrial planet. Mercury remains more difficult, but orbital missions can refine surface ages, composition, and crater statistics. Asteroid missions continue revealing what the belt looked like and how its populations formed. Meteorite laboratories can identify isotopic signatures of long-destroyed parent bodies. Every one of these measurements places another constraint on the kind of planetary system that could have existed, and then there are exoplanets. When Planet 5 was proposed, astronomers knew far fewer planetary systems around other stars than they do now. We have since learned that planetary systems can be extraordinarily diverse. Some stars possess tightly packed groups of rocky planets. Others contain giant planets close to the star. Some systems appear dynamically quiet. Others show signs that planets migrated or scattered one another. There are strong reasons to think that ejected planets exist between stars. All of this makes the general idea of a lost planet less exotic. Planetary systems do not always preserve every world they form. A solar system can begin with more planets than it ends with. That strengthens the broad plausibility of stories like Planet 5. It does not identify Planet 5 specifically. This is where language becomes important. You will sometimes encounter descriptions calling Planet V the 10th planet that vanished. That is catchy. It is also potentially misleading. The name Planet V originally refers to a proposed fifth terrestrial planet, using the Roman numeral 5. Depending on how you count planets and whether you include Pluto under older classifications, popular articles can turn it into a 9th, 10th, or otherwise missing planet. None of those labels should create the impression that astronomers once observed planet fifths. They did not. It is not like Pluto, which was photographed and tracked. It is not like Neptune before discovery, whose gravitational influence was being measured indirectly through Uranus. Planet 5 began as a dynamical proposal. The planet exists first in the initial conditions of a simulation. Researchers then ask whether the solar system behaves more plausibly with it included. That may sound less dramatic than a lost world found in ancient records. It is much more interesting scientifically, because it shows how planetary history is reconstructed. Scientists do not have to see every object that once existed. They can ask whether a missing object improves the explanation. Sometimes this works spectacularly. A hypothetical body becomes increasingly necessary until observations find it. Sometimes the body remains plausible but unconfirmed. Sometimes better models make it unnecessary. Planet Phus currently sits somewhere between the latter two categories. An additional planetary embryo beyond Mars could have existed. Long-term integrations show that such a world can survive for hundreds of millions of years. Some simulations remove it cleanly. Its instability could scatter smaller bodies. None of those statements requires extraordinary physics. What we lack is compelling evidence that our actual solar system followed that particular route. And perhaps that is the most useful way to think about Planet 5, not as a secret planet that science has somehow forgotten, not as an established world missing from modern diagrams, not as a solved explanation for lunar craters. It is a testable reconstruction of something the early solar system might have done. That may sound modest, but planetary science advances through exactly these possibilities. You build a history, you calculate what should happen, you compare the result with the solar system. Then new evidence arrives. The history survives, changes, or disappears. Planet 5 itself may have followed that final path in the physical solar system. Its hypothesis may eventually do the same, or a future lunar sample, asteroid measurement, or dynamical model may reveal a clue that makes an extraterrestrial world useful again. For now, the empty space beyond Mars remains empty. Mars completes its orbit. Thousands of asteroids move farther out. Jupiter controls much of the region beyond them. Nothing visible occupies the old proposed orbit of Planet 5. If the planet was there 4 billion years ago, the solar system has had an extraordinary amount of time to erase it. And if it was never there, the simulations have still taught us something surprising. Our present arrangement of planets was not the only arrangement gravity could have preserved for a long time. There are nearby versions of solar system history in which 5 rocky planets survive for hundreds of millions of years. There are versions in which the extra world hits Mars, versions in which it enters the Sun, versions in which it survives for 1 billion years, versions in which the known planets become unstable. The solar system we inhabit is one outcome among many physically possible ones. We cannot rerun the real beginning. We only receive the result. Mercury, Venus, Earth, Mars, an asteroid belt, then the giant planets beyond. Everything else has to be reconstructed from what those survivors carry with them. So if you happen to picture Planet 5 as you settle in tonight, there is no need to decide whether it was definitely real. You can leave that particular file open. Science does. Maybe there was once a small rocky world beyond Mars, circling the young sun for hundreds of millions of years before gravitational interactions pushed it into danger. Maybe it disturbed asteroids on its way out. Maybe some of those asteroids struck the moon and left craters we can still see. Maybe the planet finally travelled so close to the sun that it ceased to exist as a separate world. Or perhaps the entire episode belongs only to the range of histories that gravity allows but nature never selected. Either way, the question has done something useful. It has taken the familiar solar system and made it historical. The planets are not simply objects arranged in a permanent order. They are survivors of formation, collision, migration, and instability. The empty spaces between them may also have histories. And when we look at that quiet gap beyond Mars today, there is no ghost planet waiting to be photographed. There is only an unanswered question about what used to be there, and a growing collection of evidence that will keep telling us how much stranger the young solar system was than the calm one moving around us now.